Kia ora tātou. Welcome to the OpenStar Plasma Showcase livestream. I'm Gabriel.
And I'm Tom.
Very good. And we will be walking you through a bunch of stuff that's happening today. Very good. All right. I think first on the agenda, we'll give ourselves a little bit of an intro. So, who are you, Tom?
I'm Tom. I'm a senior special projects engineer.
Don't forget senior.
Don't forget the senior. Here at OpenStar Technologies. Essentially, my role has been a lot of magnet design and overall device design for future devices. So, did a bunch of work designing the junior magnet that you'll see today, but then also moving on to our next device, Tahi, and onwards towards the fusion power plants, Tamanui, and also our fusion neutron source, Maui.
Very good. I suspect there's a lot there that we'll need to explain in the not too distant future, and we will get there. I'm Gabriel. I'm the Director of People here at OpenStar. I do have some background as a physicist, but on the most part, I know nothing. So, regardless, say something particularly smart in the chat, and I'll try higher. Very good. Okay, so we should also sort of burst into a little bit of an intro about OpenStar as well. So, we are OpenStar Technologies. We're a fusion energy company here in New Zealand, in the Noronga Gorge in Wellington. Fusion energy company. We've been going for about 4 years, and this is pretty much the culmination of all the work that everyone has done here for the last 4 years.
Exactly.
We are attempting to build a levitated dipole fusion energy device, and today is one of the largest milestones on that roadmap for the entire time that we have been a company. So thank you for tuning in, and should be a bit of fun. Cool. And so what should we get on to now? I guess we might as well start with the basics. Fusion energy. What is it? Have you got a one-liner for that, Tom?
A one-liner for fusion energy? It's essentially producing power by slamming different nuclei of different isotopes of hydrogen together to produce lots of energy in the form of heat.
Yes, it's the holy grail of energy, renewable energy. It is a little bit of the dream, and it's been something that a lot of people have been working towards for a very long time, and there's still plenty of work to go, obviously. But the basic idea of the thing is that fusion energy, as Tom said, is a process for creating a large amount of energy from a small amount of fuel. So efficient, in fact, that this is the way that the sun and the stars produce energy out there in space. As is usually the case for a lot of very sort of innovative ideas, quite often we just tend to try and simulate what the universe has already decided to do. And so every piece of energy that we've ever used here on Earth has actually been produced already by the process of fusion, but it has to travel here from the stars or from the sun, and so realistically, I guess, long story short, we're trying to cut out the middleman.
Exactly.
Which is cool. And so one other concept which is pretty central to this whole thing is the concept of plasma. What's plasma?
So plasma is the most common state of matter in the universe. It is essentially when you take a bunch of gas and you get it so hot that the electrons, or parts of your atom that are negatively charged, separate from the rest of your gas. And you end up with a charged gas, which behaves fundamentally differently to just a normal gas that you find in your room right now.
Very good. And sort of fundamentally they're very, they're whizzing around at very high temperatures, high velocities. And one of the things that we need in order for a successful fusion reaction to occur is to take this plasma and make it as hot and as dense as possible, so that all the atoms whizzing around essentially collide with enough frequency and enough energy to overcome the extra forces that are in there, and also at a rate that is enough to make this worth it, right?
Exactly.
And so that is what we're attempting to do, and we're not the only ones attempting to do this. There's a sort of status quo, I guess you call the tokamak, which are these machines out there being built by a lot of very cool companies out there in the world, Commonwealth Fusion Systems, and there's obviously the big one in south of France, ITER. Ours is slightly different to that. Not too different, but different in some very interesting ways, and so we'll get into some details of that when we see more about it, I guess, as the day goes on. So is that the basics? I guess it's also important to note here, if there's anything that you'd like to know, we do actually have a live chat. I'll be keeping an eye on it. And so if anything ever doesn't make any sense at all, just send us through a question, and we may or may not ignore it, but in all likelihood, if it's a good question, we'll try to answer it.
Exactly.
That's the dream. Cool. And so, is that the basics? Did we get through the very, very...
That is the very basics, yeah.
I
think actually one extra thing I'd like to point out is a bit of a fun fact. So, like,
fun fact. We have plenty of fun facts.
So many fun facts. So we have, we said we wanted to reproduce the process that happens in the sun, but the sun is actually really not a good fusion reactor. If you looked at the power density of the sun, it is about equivalent to a pile of compost. So, like, if you were to actually try and generate a fusion reactor that behaves just like the sun, and maybe generate 500 megawatts, which is a roundabout standard for a power plant, you'd need a ball about the height of the Eiffel Tower of compost in order to do that, which is not really feasible to do on Earth. So
unlucky.
Yeah, we need to do a little bit better than the sun.
We would have tried if it was.
Yeah, we would have tried.
Cool. And so I guess, again, another important part of this, so the sun actually does this by virtue of crushing everything together with its gravitational field. We'd like to be able to just do that, but it would tend to crush everything in the near vicinity. So not a particularly feasible option. So what are we doing instead?
So what we want to do on Earth is use really strong superconducting magnets, which we'll talk about a little bit again later, to confine the plasma. So essentially, because plasma is charged, it will interact with magnetic fields. We actually see this happening around the planet. Essentially, where we had charged particles coming from the sun, the solar winds, just other places in the universe, and they come in, they are captured by the Earth's magnetosphere, and they bounce around between the poles, just doing their thing. However, when they get really hot, either through a solar storm or just because they come in with a lot of energy, their bouncing, which happens between the poles, gets further and further towards the poles. Now, at some point, they get enough energy to actually hit the poles because there's a planet in the way. And that's when you get the aurora that we're looking at right now. And we don't want that. If we want fusion, we want to be able to get these particles really hot. We don't want them hitting anything. So this is actually why our concept, the levitated dipole, is super interesting. It captures that physics that we see in the auroras and planetary magnetospheres and brings it down onto Earth. We levitate a superconducting magnet inside this is a 5.2 meter vacuum vessel that we're seeing here. And we levitate it so that there are no magnetic field lines that intersect any geometry. So essentially, we don't have the issue of if the particles get too hot, they hit the poles. We don't have any poles. There's just a big hole in the middle. So they can just spin around the magnet and keep going as much as they want, and they get as hot as they want as well.
So like if Earth was a ring world.
Yes, pretty much.
Hey, you never know. Could be pretty good. Cool, very good. All right, sweet.
Yeah. Moving on, we can actually talk a little bit about the magnet that we're using. So our magnet is a little bit special in the fusion world. So with other devices, they use superconducting magnets to contain the plasma, essentially by trying to, like holding jelly in between your fingers. They're trying to squeeze things in.
We've all done that.
They're trying to squeeze the plasma inwards towards itself. Now, there has some issues with stability and all that kind of stuff. The way that we do it, we actually put the magnet inside the plasma. Like you actually find the magnetosphere, the planet is inside the plasma. And that comes with a bunch of benefits. So one, we can leverage the fact that it's naturally stable because it's just using nature, physics that we find in nature. And, what else? It's also incredibly simple. That's the other one as well. So we only have one superconducting magnet. Other devices have many, many superconducting magnets, which can be quite expensive.
Keep it simple, silly, as they say.
And yeah, so that's sort of what we've been building, and one of the main things we've been focusing on in the past 4 years since we started at OpenStar is building this core magnet. So it's a bit of a special magnet. It's comprised of 14 superconducting coils, arranged in such a way to create this low field region inside the magnet. You can see magnet engineer Emerson here working on it. We'll hear from Emerson later. He's going to be our Levitation operator today. He is essentially working on the electronics that the low field region is put there so we can place sensitive electronics and power supplies on board the magnet that usually would not be like to be placed in a high magnetic field environment, which is convenient because This magnet will generate at full field 5.7 Tesla. However, today we're only going to be running it at 3.3 Tesla, which is still around about 100,000 times the Earth's magnetic field.
Yeah, well, we got some comps here, eh?
Yeah.
Is it? So 3 Tesla.
Yep.
I think we had 30 microtesla was the Earth's magnetic field at 0 latitude and longitude. So stronger than that.
Yeah.
Too easy, really.
Too easy.
300 fridge magnets.
Yep.
No dramas. And 2 times stronger than the strongest permanent magnets.
Yeah. So neodymium magnets are about 1.6 Tesla.
Cool.
So that's give us some.
And so we did.
Scale.
We did breeze over one thing there, which is superconductors. I'm sure there are many people listening that know far more about either superconductors than either of us, but there will be some people who have never heard of that before. So, what is a superconductor?
A superconductor is a material that can conduct electricity with zero resistance.
Zero resistance, you say?
Yes.
Like actually zero?
Actually zero resistance, among other things.
That's crazy. So I did my studies in superconductivity, and I got used to saying just the same line over and over again. It's like, we've got gold or copper that we usually use to conduct electricity from place to place. Very cool, very expensive, very good, but when you actually move electricity from one place to another, it will cause some heat to build up in that material because it has a thing called resistance. Superconductors have zero resistance, which is sick. The thing that is complicated about superconductors is they actually have to be below a certain temperature in order to work at all in that regard. And actually, with these ones, when they go above their transition temperature, they've actually got quite high resistances because they're ceramics. So they are very delicate materials, and it's kind of its own whole sort of, emerging industry, right? Creation of superconducting tapes. And realistically, it's probably the thing that has driven the sort of renaissance in fusion energy sort of private companies that have been popping up over the, last 10, 20 years in general, right? Like, I get these questions a lot where everyone's like, fusion energy has been coming every 10 years for the past 60 years. What's actually changed? Realistically, it is the advent of these superconducting tapes that we are actually able to use in applications, and we can get like kilometers of superconducting tape, which is something that's really only come around in the last 5 to 10 years, I guess. So, very important part of it. We have these electromagnets that are made of superconducting tape. So that's important. Zero resistance means we can put heaps of current through, which means we can make a very strong electromagnet, which can confine the plasma.
Yes.
I'm going to check the chat.
Cool.
I think we've got some questions. Well, there's heaps going through. Okay. I'm going to just read it out and assume we can answer it, and if we can't, then it is what it is. How are you progressing on controlling the levitating magnet within micro nanoseconds to stop it hitting the top or bottom of the container?
Oh.
You know what? That's kind of exactly what today's all about.
Yes.
So if you want to see some progress on that, probably just stick around, I guess. Believe it or not, we can do it. What else have we got? 3.2 Tesla is about equal to current state-of-the-art MRIs.
That's exactly right.
That's pretty sure. Yeah, I'll figure out other things as we go. What else have we got going on? So, superconductors, magnets, what's next on the list?
What are we doing today?
Yes.
Probably should talk about that.
What are you going to see? So thank you for that question. That led us perfectly into our next point.
Cool. So today, we'll be seeing something a little bit like this. We've got some people in there to give us a little bit of sense of scale.
They won't be in there at the time.
They will not be in there at the time. Mm-hmm. We are going to mount our magnet inside this 5.2 meter vacuum chamber. The magnet is about 1.2 meters in diameter. So the magnet we saw without its cryostat shell before, but now it has, in this photo, a cryostat shell to protect it from the plasma. We will see us raise the magnet into the center of the chamber. We will then turn on the levitation system, so we'll see the magnet start to wobble around. We'll drop away the catching system to give us lots of space to generate the plasma inside the magnet, but also mainly around the magnet. And then we will generate the plasma using approximately, I think today we're going to be aiming for around about between 5 and 10 kilowatts of microwaves. We have about 30 kilowatts mounted to the chamber, but we're not going to go for that much today.
Keep it simple.
Yeah. Yeah, so we'll be going through a full plasma shot. We'll be going through a full levitation cycle. It's going to be super interesting. It's got sort of a culmination of that 4 years of work, getting all the systems working in here, but mainly it's the core hero of the show here is the core magnet. This is one of the few HTS magnets that has confined to plasma.
Yeah.
I think.
It's definitely not common.
Yeah, it's not common at all. I can't get the number right at the top of my head. But.
And so what are these numbers that we've got up there at the moment?
Yes. So essentially we have some readouts of the live data that's happening right now. We have the current field, so about 3.3 Tesla, with the current inside the magnet, so 741 amps. So this, to give us a sense of scale, is the standard wall outlet plug is rated, in New Zealand anyway, is rated for about 10 amps. So this is about 74 times?
Yeah, a lot more than that.
74.1 times the standard current you get in the cable that you get to your appliances at home.
We've got the operating temperature there at the core magnet, so that's approximately 33 Kelvin, which we looked up just before, is pretty much the temperature on the surface of Pluto.
Exactly.
So that's pretty cold.
It's very cold.
And so what temperature what actually is the transition temperature of these superconductors? They have to be below something like 90 Kelvin in their like pure state. So we're operating at significantly below its transition temperature because obviously you don't want it near there, otherwise it will heat up, stop being superconducting. It's got heaps of current going through it, and it will stop working. You'll burn it.
Yes.
Which is not what you want. Cool. And so the next box down, the HTS power supply.
Yes. So this is one of the other new things that we've got going on here. So HTS power supply is something that we can take advantage of with a superconducting magnet. So to supply that 700 amps of current, or at full field, it'll be 1.5 kiloamps. And then for future devices, it'll be in the tens of kiloamps. So we're going to get bigger and bigger as we go along. To supply that normally, you need either a power supply that's like the size of a room to supply that kind of current. But we can't do that. Since we have to levitate this with no physical supports, we have to have all services on board the magnet in order for it to function properly. So in order to do that, we need to use a power supply method that uses superconductors. Otherwise, we'll generate too much heat on board. So what we have right now is we have a set of batteries, it's batteries right now for fusion reasons. We might switch over to some other energy storage method on board the magnet, but they will supply a small current at a reasonable voltage to the HTS rectifier. It would then go through a transformation process where it will get transformed to a really high current, low voltage alternating current, and then we have some superconducting switching elements that will convert that to a nice DC signal that we can then use to charge the magnet. And this is one of the key things. This is the key enabling technology for a dipole.
I think this is pretty safe to say that the power supplies are our speciality, really, right?
Yes.
So Ratu, our founder and CEO, was doing his doctorate in these power supplies at the Robinson Research Institute here in Petone in Wellington. And so I guess it sort of planted the seed for this iteration of the levitated dipole to re-arise, so to speak. So previously, this levitated dipole concept was being studied at MIT and Columbia University in the LDX experiment, and that was before high-temperature superconductors. They were using low-temperature superconductors, right, for their magnet, and they also didn't have these high-temperature superconducting power supplies. So one of the things about a levitated dipole, particularly like in contrast to a tokamak, tokamaks have their magnets on the outside of the burning hot plasma, which means they have all this space along the outside to provide things like current, connect to all the auxiliary systems that you need in order to run those magnets. With the levitated dipole, because we have the plasma on the outside of the magnet, which is very desirable for a number of ways, it means we're very spatially constrained, right? So these power supplies being on board are one of the key things that has enabled us to revive this concept and have another hack at it.
LDX was a sort of pulse device in many senses, but one of the ones was that we would lift it, we would let the current, it would charge it once, and let the current decay, and then they would have to recharge it later in order to do another pulse. For a power plant, we can't have that kind of downtime. So essentially, even though we will not be seeing that today, we will actually let the current decay today to, once again, keep things simple. This magnet has been charged with the power supply. It is currently running. We can see the state of the power supply is on. We'll hopefully in the next few minutes see that turned off as we start to pre-cool the magnet for the levitation attempt. But essentially, what the power supply allows us to do is, in the proper functioning case, is actually let us to maintain the current at a constant level throughout the entire operational life of the core magnet in a power plant. And that will allow us to essentially keep it going and keep our downtimes really short. Because we still need to dock it every so often to make sure we extract all the heat and all that kind of stuff and recharge the energy storage on board. But that can be a really quick process if we're not trying to charge the massive inductance of this magnet.
And it's also worth saying, when at some stage when we switch over to the control room, you will see a guy called Darren talking a reasonable amount. He was actually the chief experimentalist on the LDX experiment, so we're very lucky to have him around as our chief science officer and transferring a lot of that knowledge and making this possible. He's the levitated dipole champion of the world, potentially. Cool. And so we also have the top magnet there. Status green.
Everything's good.
That's the dream.
Good. If it was anything else, we'd be a little bit upset.
Very reasonable. And that is very cold.
Yes.
Colder than Pluto.
Yes, that is very cold. So essentially, actually, we haven't even mentioned the top magnet. We've only been talking about the core magnet, which is our sort of pride and joy. The top magnet is what we need to levitate this magnet. So there is a second magnet on the screen right now. We can see the sort of inset area, that big piece of metal at the top of the chamber. This is where the top magnet sits. It will be charged to around about 2 Tesla for this state. It will be lower field for stronger magnets because we need to generate less force. But essentially, that is a totally different magnet topology. So our current core magnet is a non-insulated magnet. So essentially, all the turns are soldered together, and we rely on the fact that the superconductor has 0 resistance to make sure that we don't have an electrical short through all the turns. That's great for steady-state magnets like the core magnet because it achieves, you can get much better cooling and also better quench protection if things were to go wrong. The top magnet, however, is going to be an alternating current magnet. Essentially, it needs to change the current rapidly in order to arrest any changes in position in your core magnet. And so because of that, it is a very different construction. So instead of being the turns soldered together, it is wax impregnated.
Ooh.
Yeah. Which has been really cool. We've broken this magnet a few times, but that means that we can actually recycle most of the tape. So this is the 3rd iteration of our top magnet. We've broken it a few times before, just doing random tests and pushing it to its limits. Today, the current magnet we have in there is 95% recycled tape, and the rest of it has just been sliced in there to repair all the damaged bits, which has been something that we can only do with a wax-impregnated coil.
We're really quite proud of that as well.
Yeah.
Recycling a quenched superconducting coil and reusing it for the 3rd time.
Yes.
We're very happy about that.
Yeah, we're very happy about that. Cool. So everything's looking good. It's a lot colder than the core magnet, mainly because it's a much simpler design. So the core magnet was also... Well, there was a few things. The core magnet, one, is not attached directly to a cold head, to the cooling system like the top magnet is, because it can be accessed by external services. The core magnet, as we'll see in a little bit, is cooled through a supercooled helium loop. So we will actually see the undocking process in approximately 45 minutes. We've got the T-minus countdown happening there. That's when we're going to start undocking the magnet and stop cooling and start all the fun stuff that we're looking forward to seeing today.
Oh, we've got some action in the chat. So someone was saying, how do you cool it? Is it internally cooled? And then we've got one comment that says, surely that would mean you'd only be able to do a shot for less than a few seconds before you saturate your heat source. And again...
That's a good question.
You want to take that one?
Yeah, we can take that one. So, essentially, we're relying on centripetal forces, or like of the plasma, to keep the plasma away from the core magnet. So, plasma is spinning around the magnet, and because it's spinning around so much, it essentially acts like it wants to expand away from the magnet. It always wants to expand away from the magnet. We have this... I don't get too technical into the actual physics of the confinement of what's going on here, but essentially we have this inwardly pinching effect that pushes everything inwards, but at some point, that inward transport balances out with the plasma wanting to expand outwards, and we end up with this peak in the center. And that is sort of... We end up not actually having any heat being deposited, or in this case, we will not be having any heat being deposited in the magnet.
You know what? I also won't explain the physics of that one. It's not because I can't. It's just, I just won't. Cool.
Yeah,
All
yeah.
right. Sweet. So, yeah, there's plenty going on in the chat. And so where are we up to? Have we talked about the vacuum vessel yet?
No, we haven't done that yet.
That's a good one.
Yeah.
Next on the list.
Beautiful vacuum vessel. Essentially, this is a 5.2 meter, 12-ton vacuum vessel that we got delivered in 2023. So on Halloween 2023, we lifted this up on a crane and pulled it through the roof, which is a very fun day for everybody here.
Shout out to E-Tech.
Shout out to E-Tech, yeah. If you're watching this, it's been an absolutely fantastic chamber. Had no issues with it.
Yeah. And it came in on Halloween, was it 2023?
Yeah.
Which was cool because Halloween 2024 is when we managed to do our first plasma pre-levitation.
Yes, so supported.
Yep, which is a big boon.
Yep.
In fact, if you've ever seen the video of that, you could see exactly how happy we were when that happened. Shout out to James running around and being very exuberant. And we kind of just missed Halloween again this year.
Yeah.
But yeah, you never know.
Last
Halloween.
year.
yeah, this year. Exactly, 2025. Oh, sweet as. So those are the main specs there.
Yeah. I mean, we're talking about the pressure. There's also another fun fact there. So at room temperature, this chamber contains about 50 kilograms of air, or nitrogen in this case. But as we pull out the air, so at the pressures that we're reading right now, so around about 1 times 10 to the negative 7 millibar, it contains 5 micrograms of gas, which is about a hundredth of a grain of salt.
Whoa, good quick math there. I appreciated that. 100th of a grain of salt.
Yeah.
That's pretty small.
Is the mass of gas that's in there.
Really?
Yeah.
Do you know like how much? So this is an important part about fusion energy in general, is that it only requires a very small amount of mass to be put in to produce energy coming out, right? And so in the future, we're aiming for DT, right? Deuterium, tritium. How much generally will get put in? Is the amount of fuel that we put into a levitated dipole going to be similar to a tokamak or any of these other ones, or is that?
Yeah, I think we're going to be a similar amount of fuel. Yeah.
Cool. Sweet as. And so I guess it's also reasonable at the moment to give a little explainer on the what's actually going on in our progress bar down the bottom. So we are stop charging at the moment.
Yes. So this is our pre-cool stage. You can actually see, if you're paying attention, that the HGS power supply has been turned off. It's now cooling down. We've turned off all the heaters. Everything is now in its standby state. And we're doing this because the power supply, even though it's much more efficient than a room temperature power supply if we were to do the same thing, still produces a lot of heat. And for for this experiment, we want to maximize our levitation time because the magnet's quite small. We don't actually have that much thermal mass on board. So we actually want to maximize that to get as much plasma shots as possible, to do as much physics as we want to when we actually want to do the physics. So what we're doing right now is we've turned off the HGS power supply and we're just going to let the magnet cool down. Hopefully we'll see it drop below 30 Kelvin, which will allow us to give us like extra 10, 20 minutes while we're levitating to just do as much as we want. Although today we're not going to be maxing out the full levitation time. This magnet we've designed here can levitate on our record for about 90 minutes. We can stretch that to 2 hours depending on how things are going. But today we'll just be doing, it allows us to do around 12, possibly more if we're really onto it, plasma shots. But today we're only going to be doing 2 or 3 depending on what the control room decides is appropriate before we move through and continue with our schedule.
Very good. And so we've gone through the basics of what this machine actually looks like - is.
Yes.
It might as well be a good time now to plug a little bit what the difference is between our machine and the other ones that you might hear about being built around the world, right? So as far as I know, we're talking in things like quasi-stability of the plasma and our ability to iterate. Do you want to? Where do you want to start?
Cool. I think stability is kind of fun. So with a lot of other devices, it is, as I think briefly mentioned before, like trying to hold jelly with your hands and squeezing. It will just go through all the gaps.
Yeah.
And
you try and squeeze it, and it comes out the gaps, and then you need someone else's fingers to go in and squeeze the bits coming out through the gaps, and then it just keeps coming out, and you end up with quite a few pairs of hands.
Yes, exactly. And on top of that, it's also really energetic, so it really wants to escape through all those gaps and like sort of bend in weird ways and do all that kind of stuff. So tokamaks do have some pretty bad instabilities that will cause the plasma however hot it is at the time, to smash into the walls and cause some damage, which we do not want to do. And for a power plant, it's all about uptime. So there was a pretty complicated control system on there. Stellarators are another common fusion scheme. They use very complicated magnets. They don't have the same stability issues.
They're crazy, eh?
Yeah,
everyone should definitely Google stellarators and
it's nuts.
because those are pretty sick.
Yeah. They are very stable. However, they are quite complicated. So essentially, a dipole is the best of both worlds. It is stable and is extremely simple. So that stability means we can have extremely high uptimes and not have any damage in the best case scenario. We're essentially swapped out from plasma stability to making sure we levitate this magnet, which is a much easier problem. I'd like to point out the timescales of this thing moving are way slower than a plasma moving because of the higher mass. So actually, that's a good point. I didn't point out how heavy this magnet is.
Oh yeah, hey Tom.
Yeah, hey Gabe.
How heavy is this magnet?
This magnet is 560 kilograms. So we will be levitating that today, which is pretty impressive.
Yeah.
Yeah.
That'd be pretty cool to see.
Pretty cool to see. Anyway, that mass gives us quite a bit of inertia. So when we actually do our levitation control, it's quite slow in comparison to something like a plasma. It is still quite a fast control system, I'd like to point out.
So I'm not a plasma physicist.
Yep.
So the concept of stability in a plasma is obviously very complicated. There's all sorts of instabilities that can occur, and you can, it sounds horrific. The way that it was explained to me as a physics educated layman, it was instead of like if a unstable equilibrium is trying to balance a ball on top of a hill and it can go down either way, our situation is more akin to balancing the ball on the side of a hill.
Yes.
Where if you keep pushing it up, it's going to actually stay there.
Yes.
As soon as you take away that force pushing it up the hill, it'll roll back down, but it's still relatively predictable.
Yes.
Right? Is that reasonable?
That's reasonable. That's a reasonable analogy, yeah. So essentially, that's one of the nice things about fusion as well, in comparison to fission as a power source. And when we turn off the heating systems, this will turn itself off if we design it in that way. And also, brain freeze.
In terms of like turning itself off, I think I've heard Ratu say a lot, and it makes perfect sense. It's like fusion's really hard to do.
Yes, that was the point I was trying to think of. Yeah, it's really hard to do.
It's not something that's just going to keep going no matter what you do.
Yeah.
We have to try very hard to confine this plasma in the first place, particularly at enough, making the plasma dense enough so that you get enough of these reactions occurring to actually get enough power out to make it worth it. If something goes wrong, it's like what will happen is that it will stop fusing, because fusing things together is very hard to do.
Exactly.
Much like shooting two bullets at each other.
Yeah.
Mythbusters have done it. But
Yeah.
Cool.
Yeah.
And so, very good. So that's a little bit about stability. The other thing that is important and very closely related to what you're saying already is our ability to iterate. Right?
Yeah, exactly.
So this is a point that we try and make quite a lot because we think it's really important. Because we only have one core magnet, which we can just put inside this vacuum chamber, turn on, test. We can essentially just work on, say, two of these at the same time and design, iterate on the one that's not in there and swap them out on a sort of 3-monthly cadence or something along these lines. Sounds simple, but on the scale of like these machines, tokamaks and stellarators, etc., they're such complicated machines that if something needs to be tweaked, you can't just like take all of these 5 meter high superconducting coils, one of how many in like 12 to 16 or whatever superconducting coils on the outside of these massive tokamaks and tweak it and put it back in. We're obviously like part of the second generation, I guess the second wave of fusion energy companies, and so we need to be able to iterate fast, we need to catch up, and we think the fact that we just have this one core magnet which can, like I said, essentially we could have 5 of these and design iterate on all of them and just sort of cycle them through, right? So we think that is a very important part of us being able to sort of catch up in this fusion race.
Yes.
Which is pretty cool.
Yeah. And as Gabe said before, the key enabling technology is the power supply as well, which is New Zealand specifically is a world expert at.
And so, like, that's all rosy.
Yes.
Which is cool. And obviously there's trade-offs in any machines. People don't just like pick one machine for the sake of it just because it's people building other machines also have their pros and cons. I guess the hard part about our one is really that engineering of the core magnet, right? Like, as I said before, very confined space. And so I think, as Jerome pointed out in the chat, like, this is a proof of concept that this, the ability to have a superconducting core magnet with a high temperature superconducting power supply, and you can keep it cool for long enough to shoot your shot on a couple of plasmas. So that's like the proof of concept that we are demonstrating today. It's probably quite important to point out what we're not doing, right? We're not saying, hey, net energy gain, which is what everyone who sort of tunes into Fusion Energy News would be expecting to see for a big thing, right? Like, that is a little way off. It takes, as we say, probably quite a few design iterations before you get there, and everyone's trying to get there. It's the holy grail. But this is the first step, a proof of concept that this works in general, and we have like a 4 machine pathway, which is, we build this one, this is called Junior, our next machine is going to be called Tahi, which is basically scaling all of this up. How strong are we hoping the Tahi core magnet to be these days? 20 Tesla?
Yeah, 20 Tesla. Yeah, so it's a much stronger core magnet. Same size of device and vessel, as just essentially to get the plasma really hot, test our magnet design chops, make sure we actually have a design that can scale up to the physical sizes of magnet that we need to build for a power plant, and also the field strengths that we need. So it's essentially a test bed for all those things, and also just getting the plasma really hot, getting a few fusion reactions, not that many, but actually probing the physics in a way that hasn't been tested before.
And eventually we will get to the stage where we produce our final machine, Tamanui, which is, what do they call it? First of a kind?
First of a kind.
Which should be a bit fun, and that's a little bit in the future.
Yes.
And that'll be fine. It'll be easy. No worries. Cool. Okay, I think we've got through the majority of what we definitely said we'd talk about. Key differences, what have we done, you're about to see, and what to expect. So I guess, it's probably worth just reiterating what people will actually see for those who have turned up in the last wee while.
Yes, so checking on the countdown timer, we've got about 32 minutes before we start our undocking procedure. So we'll watch the undocking procedure take place. It will be...
The undocking procedure?
The undocking procedure.
What is that?
So that is, we had a question before about the cooling of the core magnet. That was, at the moment, the way we're cooling the core magnet is through a supercooled gas of helium. This is pumped through the magnet at high pressures just to transfer transfer the heat out of the magnet and out towards the cooling system that we have hooked up externally. This is connected through some big long tubes called bayonets. We'll be talking about that in a bit, which are vacuum jacketed and sort of designed in a way to not puff a bunch of helium into the vacuum chamber, which would not be great. This will have about 30 to 45 minutes of this procedure, where we'll have a team down underneath the chamber. We can actually switch to that view now, just to give people an idea of what to expect. Under the chamber to extract the bayonets, which you can sort of see to the left and right of the center of the camera, and turn off all the cooling systems. This will be, pretty exciting. It's quite cool seeing them do the work.
Living the dream, so to speak.
Living the dream. So it's also worth talking about, like, this will not be what we do in future devices. This is just something we did to make it quick, because once again, we wanted to test the core magnet was being the design focus of this iteration of this device. In future, this will be an automated process, which we can do really quickly. So after this, we will then bring up a view of the side of the chamber, and we can start doing the levitation and plasma shots. Cool. This is a live view from inside the chamber at the moment. We can actually see some of the cryo pump, which we'll talk about again later. So one of the 2 vacuum pumps. This will be important when we start running the shots. Those will be opening and closing, and you can use that as a gauge to whether or not we're about to go for another shot or not. So down the bottom there's the core magnet,
which is basically the whole thing. And up the top, we have our top catcher, the sort of cone top catcher, right? I think we had some questions about catching, etc.
Oh, yes.
Like, the top catcher, very important.
Yes.
And I didn't immediately click on this when we were working on it before. I was like, why is the top catcher so much different to the bottom catcher? And the idea is, there's a huge magnet at the top, and there's a huge magnet in the middle. If it decides to fall towards the top, those forces are going to get bigger and bigger and bigger as they come together. So it's very important that we're able to catch it from the top.
Exactly. So essentially, when it's in the correct state, it's generating about 500 kilograms of force upwards, those two magnets. When it gets further up, it gets almost exponentially more power. Like the forces pulling together get exponentially stronger. So we really want to arrest that before it gets too strong and make sure that the g-forces on the magnet do not exceed what it was designed for. Hopefully, we will not see that today, even though it would be kind of fun. There are some great videos of LDX, pretty much our predecessor at MIT, dropping and slamming their magnet up towards the top, and amongst a few other things that Darren doesn't want us talking about.
Yeah, fair enough. And so I'll come back to a couple of these chats here. We've got how you're progressing on the next size vacuum vessel. I think you mentioned that the next vacuum vessel is really not going to be that much bigger.
Not that much bigger. So it'd be 6 meter diameter instead of 5.2 like this one. So not that much bigger.
And also would just like to respond. James Rice says, Kia ora te whānau from the marathon offices in San Francisco. That's pretty sick. Hope you guys are having a good time watching. And we're getting a good number of just compliments on our chat. Very good. We've got one. OpenStar podcast we're at.
Oh, yes,
yeah, surely it's and also great chat and really appreciated from Andrew Swanson Dobbs, which can only be related to Emerson.
Yes, the man himself.
Very good. We'll see a lot of Emerson in the not too distant future. Cool, sweet as. I think it could be a reasonable time for us to just drink a little bit of water and maybe check in on the comms, see if there's anything going on in the control room. I don't know. Should we give it a go?
Let's give it a go.
Try to turn it down so it's not crazy. All right. Very quiet chatter in there.
Yes, so we are still in the pre-cooling stage, so there will not be that much chatter until we get to the next state, which is the sort of facility prep and top magnet prep.
Okay, very reasonable. All right, well, let's just have a 1 or 2 minute break.
Yep.
And you'll hear from us in the not too distant future.
Tom needs to hear us.
Alrighty, we're back. So, we've had a few more people join the stream since we started. So, it might be worth going back through a little bit of what we've already said from the start, just for the people who missed the beginning. So, again, welcome to the OpenStar Plasma Showcase live stream.
Exactly.
Who are you?
I'm Tom. I'm a Senior Special Projects Engineer here at OpenStar. Essentially, my role has been a lot of magnet design, a lot of other just overall device design. So essentially, did a bunch of design on the Junior Core magnet, which will be seen today, and also the future devices such as Tahi, which we'll be building next with a much stronger magnet, same size. And then also moving on to our proper fusion devices, Maui and Tamanui.
How good. And I'm Gabriel. I'm the Director of People here at OpenStar Technologies. And so we are two of about 70 people that are working here these days, including about 10 interns, which has always been fun. And so, we're still a pretty young company. We've been around for about 4 years. I guess we could do a little bit of lore even, right? Yeah. So OpenStar was started. I was actually living with Ratu at the time before I ran off and started teaching physics in the Pacific Islands and then came back eventually. But Ratu and Al was living at Alice Street, and also James Rice, of course. James and Ratu were both doing their PhDs in applied superconductivity at the Robinson Research Institute. And Al, who is our president, was working on general relativity. So he's also a pretty crazy thing. I guess, realistically, founded by a bunch of physicists. I was there doing my studies on iron-based superconductivity, which kind of went nowhere. But that's okay. I'm but a material scientist.
Yes.
So we've been around for about 4 years. And this is, again, the culmination of a bunch of people's very hard work. You'll see a lot of them in the live stream coming up, and we'll sort of tell you a little bit about the people that you see, but it's also worth reiterating that there have been a lot of people that have worked on this. There's 60 to 70 at the moment, but there's probably been another 20-ish that have come and gone, and internships and all sorts of consultancy as well. So this is a really big moment for everyone here. So I guess shout out to all the OpenStar peeps.
Yes.
In particular, fantastic. Hey, good job.
Good job, everybody.
Is what we say to that. Yes. And so, yes, again, from the start, we are working on our fusion energy levitated dipole device. Fusion energy, the basics. We want to produce a plasma, the fourth state of matter, the most abundant state of matter in the universe.
Exactly.
Right? All the stars and all the stars and all the suns is what I was about to say. All the stars and the sun. Produce energy through the process of fusion. We need to create a plasma, which we do by virtue of heating things up a lot, right, and stripping the electrons off the atoms that are around. It's usually hydrogen, helium. And if you make that plasma hot enough and dense enough, then those particles are whizzing around with such velocities, and there's so many of them in such a small amount of space that they'll hit each other and fuse at a rate that is capable of producing more energy eventually than you put in, is the idea. It's the holy grail of renewable energy. We're not the only ones working on it, but we are working on a particular sort of geometry-design called the levitated dipole.
Exactly.
And I guess, essentially what that comes down to is we've got a pretty stonking magnet, 500 kilos. 5.6 Tesla, it's rated to?
5.7 Tesla.
5.7. 5.7. Today we'll be operating at around
3.3. Oh, sorry, around about 3. So we have stopped charging.
Nice.
We have stopped charging. So it has decreased. We were at 3.3 at the start of the stream. We're now at 3.2. We'll probably decrease to about 3 Tesla throughout the course of the day.
Yeah. And this is a superconducting magnet. It's made of what? How many coils?
14 Rebco coils. Rare earth.
What's Rebco?
Rare earth. Was it barium? Copper
rare
oxide?
earth, barium, copper oxide. That's the one.
That's the one.
Is it yttrium in particular?
This one's yttrium.
So superconducting tape, how much of it?
On the order of a kilometre. I can't remember the exact number.
Yeah.
I should have revised that before the stream, eh?
Yeah, so a kilometre-ish of
Yeah.
superconducting tape. Superconducting tape's not cheap,
Yeah, it's not.
and well, I guess in the future it will become
Yeah,
cheaper
it
and
is
cheaper
becoming cheaper and cheaper quite quickly.
because the production of superconducting tape is relatively new to the world, and is a very important part of why the fusion industry in general is seeing this sort of renaissance,
Yes.
so to speak. And in terms of OpenStar, why we've ended up where we are, like a lot of us did come out of the Robinson Research Institute, which is specifically aimed at applied conductivity, right? So it's not, people always ask us like, oh my God, in New Zealand. It's not like just a bunch of superconducting experts all just decided to move to Wellington and met at the pub and started a business. Like it came out of a lot of work that's been going on in this realm in Wellington for quite a long time.
Yeah, exactly.
And superconductivity, very much our area of expertise. HTS power supplies in particular.
Mm-hmm.
We've been through a little bit of details on that already.
Yeah. New Zealand's also been constructing high temperature superconducting magnets since 2004. That's another
Since
one.
2004.
Yeah, HTS 110.
Shout out
HTS
HTS 110. What good people. But yes, so it seems like superconducting expertise is a growing sort of specialty in New Zealand. So it's like we're not the only ones that have this sort of knowledge, and it's really cool to see a lot of other companies around New Zealand doing similar things. And hopefully, one big ecosystem.
Yes.
Open ecosystem. Very good. All right, and so we can go back to the metrics that we've got up on the thing at the moment. Has anything changed in the not too distant past?
Nah, these are all been pretty stable. One thing we could point out is that the pre-cooling stage is almost complete.
Mm-hmm.
We have essentially the magnet started at about 32 Kelvin. We've now subcooled it about a few extra Kelvin just to give us the extra little levitation time, just to make sure we're not time pressured in any way.
The temperature on the power supply has changed from when it started. That's because we're measuring from a different place now, or
I know it's the same place,
Okay.
but the power supply we need to turn heaters on to make it work efficiently.
Ah.
So essentially, it's heated above the temperature of the rest of the core magnet to make sure that we can actually turn the superconductor off. Superconductor is one of those things where, like, as you make it colder, it can reject magnetic field better and can have higher critical currents. But if you want to switch it off, that's bad. So you want to get it quite hot, and the scale of superconductor, 70 Kelvin, which is still negative 200 degrees, so still quite cold, but warmer than the rest of the magnet. We want to get to that temperature so we can turn it off quite easily, because the maximum temperature of these superconductors is around 90 Kelvin. At 70 Kelvin, they still have quite good critical currents, or current capacities, I should say. But we can apply a moderate magnetic field to them and turn them off and generate nice voltages that way to actually make it a power supply.
Oh, how good. Okay, and so levitated dipole, we can reiterate a little bit of the differences between this machine and some of the other ones. I'm sure we have a few pretty avid fusion aficionados around. So, here we go. Here's Emerson. Hopefully Emerson's dad, maybe, is still watching. There he is. What a good guy. So he's working there on our core magnet, which is the very central part of everything that goes on here. And one of the key differences between our technology and something that you might find in another fusion energy design is that we only have this, we've got the top magnet and we've got this core magnet, right? And so this magnet is the one that's doing all the confinement.
Yeah, the key thing is that the magnets are not sort of wrapped around the vacuum chamber.
Yeah.
We have this one magnet on the inside, which is totally decoupled, and then we have one magnet, or maybe a few more in future devices, but essentially none of them are wrapped around the chamber. They are sort of in their specific areas. But essentially, in this device, we have two magnets. We've got the core magnet, which will be Levitation. That's the 560 kilogram, 3-ish Tesla currently magnet that we can actually see in front of us right now that Emerson is working on, comprised of 14 superconducting coils, non-insulated, so the turns are physically soldered together, and we rely on the fact that the superconductor actually has truly zero resistance in order for it to not short the turns. This has been great for a variety of reasons, but the other magnet, the top magnet, is a much smaller magnet. It is insulated, so it's actually a wax-impregnated magnet, and that allows us to recycle it and decrease iteration times. And that we don't have any photos of, unfortunately, but that will be placed in this little sort of inset region in the chamber, and that is what we are using to control the levitation system. So it can change current quite quickly, react to any changes in position of the core magnet, and we can use that to make it levitate and do all that kind of cool stuff.
I guess one question that would be kind of reasonable is like superconductors have zero resistance, which means they keep all of their current,
Yes.
right? It doesn't degrade. But we've talked about using the power supply to top up,
Yes.
right?
Yeah, that's a good question.
So that implies that it is losing some energy.
Yes.
But superconductors are, what's the deal?
So superconductors themselves have zero resistance. However, you need to connect them to other things. And as of this point, we have not figured out how to make good superconducting joints. At the moment, so we have these 14 coils. These coils themselves have essentially zero resistance, but we still need to get current into and out of them. And those terminals are made of copper. So they will have some resistance. We're using the fact that the turns are superconducting to spread that current all the way around the circumference, so the joint area is huge. So the resistance is low. This magnet has a resistance of a few microohms.
Have we got any comps on that? No.
I did not put any comparisons to that.
Like a millimeter of copper or something?
Yeah, something ridiculously small amount of copper in a normal cable. That's still really low resistance. So, for example, we can actually see the voltage that it's generating. So this 720 amps is being discharged through the magnet, and it's generating about 0.2 millivolts, which is very small. So yes, even though superconductors themselves have zero resistance, the way we have to connect the superconductor together will have some resistance, and that's why we need the power supply. It's just that, those connections are still quite low resistance, and if we were to make this entire thing out of copper, there'll be really lots of heat load being generated through there.
We've got a good question here. Hey, I have a question. Thanks, Kenny Charlton. I have a question because you're a physicist, right? How do they make those crinkle cut chips? I've always wanted to know.
That's a great question.
Yeah, that's beyond me.
It's also beyond me. I think that's a different kind of physics, man.
Sorry, mate, we couldn't help you with that one, unfortunately. Hey, what can you do? Should we check in with the control room and see if we can hear anything that's going on? Is that a reasonable time?
They're
now?
not talking at the moment.
They're not talking. I'm always over eager. It's okay. Do I have time to vacuum clean the lounge? Another important question.
Oh, yes. So we have our current countdown is we're on target for undocking starting in about 12 minutes. So if you can do it in 12 minutes, go ahead.
Yeah, you should be able to do that. No dramas. Oh, that was my sister. Yes, Valletta, you can probably do that. Is the helium doped with anything else?
No. So this is for the cooling.
Don't know.
I'm assuming. That's the only time we've mentioned helium. The helium is just pure helium. We use it because it can get really cold. Helium doesn't actually freeze. It will only ever turn into a liquid. But we're at the 20 Kelvin or below that we're using to cool the magnet. Where it's still a gas, and that makes it really easy to pump around. It's one of the few gases that can still be pumped around. Hydrogen is another one, I think, but it gets quite kind of hard to keep it gas because it does turn back into a liquid quite soon. Shortly after.
Cool. And another question we've got here. The levitating magnet is battery powered. Is it an option to power it wirelessly through the changes in the magnetic field, or is this not an option?
It's something we've thought about.
Yeah?
Yeah. So the plasma does act as quite a good shield for any sort of variations in electromagnetic field that you would need to produce in order to charge this magnet. Additionally, that's pretty much the main reason. So you could either do really high frequency stuff, so essentially point a laser at the magnet and fire energy through that way, but that would be quite low efficiency. So it's way more efficient to have the power supply on board and then occasionally recharge some onboard battery or energy storage. Additionally, that doesn't solve the main problem, which is actually trying to get heat out of the magnet. So because of all the joints that we were talking about previously, just before, and the power supply on board, but mainly the joints, and also some heating from the radiation that comes off the fusion reaction while it's running, we will need to dock this magnet every so often. Or not this magnet, a actual proper fusion power plant device. We'll need to dock that every so often to actually get the heat out of the core magnet. So the heat is the actual thing that causes us to want to redock. We could probably figure out a way of making it truly steady state if we didn't have to get extract the heat. But because of the heat, we're going to be pulsed. And since we're going to be pulsed anyway, we may as well have just onboard energy storage and use the power supply to keep it topped up.
Speaking of heat,
Yes.
How do we get the heat in the plasma? I assume it doesn't just start off 1,000,000 degrees.
No, it does not. So what we have strapped to... there are many ways of heating plasmas, but the way we've got set up at the moment is essentially two very strong household microwaves. So the microwaves that you have at home operate at about 2.4 gigahertz. That frequency of electromagnetic field gets passed into a bunch of stuff, and that will make the atoms vibrate and heat up your food at home. In this case, we have such a low pressure of gas in the chamber that that vibrating actually causes the particles to move around quite a bit. They will knock into a bunch of other particles, causing them to heat up quite a bit as well, and essentially get the plasma really, really hot. So on the scale of powers as well, we're a little bit more powerful. So your microwave at home is about 2-ish kilowatts, depending on which one you have, maybe a kilowatt. But these microwaves, we have about 30 kilowatts hooked up to the chamber. We'll be using around about between 5 and 10 kilowatts, depending on what shot Craig and Darren decide to do today.
Good old Craig and Darren, eh?
Yes.
Always living by on the edge with Craig and Darren. And I assume the hotter it gets, the harder it is to confine, right? Like there'd be an upper limit of sort of temperature that we're able to confine at the moment. Not that I imagine we know what it is. Oh, I don't even know.
Yeah, so the hotter the plasma gets, the more it tends to want to expand. So this is something that we can get into. It's a little bit more plasma physics-y, but for a dipole specifically, the hotter you get the plasma, the more it wants to expand outwards, and because of our confinement physics, that just makes the energy we can store a lot worse, or the peak pressures that we can get a little bit lower. So essentially, the way you combat that is by building a stronger magnet. So that's why, to build the next really hot, go the step up and get the hotter plasmas, we need to build a much stronger magnet in order to do so. We could technically, if we had the correct heating systems for this magnet as well, we could get things a lot hotter. However, that's not been the focus of this device. It has just been the core magnet engineering, and the plasma's just been the cherry on top, just to make us feel excited.
Yeah, nice.
Yeah.
Cool. So yeah, I think again, reasonable point to reiterate like what this is and what this is not. There's this proof of concept for the combination of the magnet technology, the power supply technology, the cryogenics. Proof of concept that this design topology works at all, right? Yeah. And again, not attempting for net positive or anything along these lines. That's in the future. It's next on the list.
Yeah.
Cool. Okay, so how long have we got? We've got 7 minutes.
Yeah, that's 7 minutes. However, I have not heard them start the top magnet levitation prep stage, so I think we might be a little bit delayed.
Okay.
I might go out and double check how things are going. So,
very reasonable.
Yeah.
Let's just have a quick break, hey?
Yeah, have a quick break. I'll come back to you in a second.
Chat. time for an update, Tom. How are we looking? I got him while he's eating a sour worm.
We're looking good. So I thought we were delayed before, but it's actually because while we were talking, they actually went ahead and finished the top magnet prep stage while we were doing that. So actually just waiting for just as long as they can get for the magnet to cool down as much as they can. So yeah, it's like at 29.2 Kelvin at the moment. That's very cold.
Cool. So classic jibber jabber from Gabe. Went
Yep.
right over all the comps.
Mm-hmm.
And so what did you just say? Where are we at now?
So we're at 29.2 Kelvin.
Cool.
That's pretty much, they want to get maybe a few more tenths of a Kelvin out of it before they start, but they're pretty happy and they're pretty ready to go.
Cool. And so in the process, we're going to undock, right? We're going to disconnect from the cryogenics and the power supply, etc. Well, not the onboard power supply, but you know what I mean. In terms of these like operating specs, how are we expecting these to change over the sort of like course of the hour afterwards, right? Is there like a temperature at which we stop, or like how do we decide how much time we can go for?
Yeah, so the magnet is designed to operate between 30 and, we're below 30 right now, but essentially it was originally designed to operate between 30 and 50 Kelvin. Essentially, we'll cool it down to 30 Kelvin, let it warm up to 50 Kelvin, and then we're all good. So that was at full current. So we're not even at full current. So we're being very conservative with our levitation times. So when we say we've got, 2 hours of levitation time, that's at this current. So it'd actually be a lot better if we were to let it go. Yeah, so it's essentially, we want to bring it down and make sure that the magnet doesn't warm up too much while we're docking it. And when we pump in all that slightly warm helium that we have just sitting in the lines, we don't have a pre-purge system set up. So essentially that will be passed through and warm up the magnet a little bit more. And then it will start decaying, cooling down a bit after that. But that's the main thing, is like the temperature is the thing that limits this magnet. The currents will drop to around 700 amps. Will still be about 3 Tesla. It's a very low resistance magnet.
Cool. And so I guess we got 2 minutes. We could just plug the papers a little bit at the moment as well.
True.
Right? Like, why not?
Why
Did it
not?
a couple of times. So like for people who are really interested in knowing more about where these design specs come from, or the actual outlook is, there's places to check it out.
Yeah, exactly. So at the moment we have a few papers published and accepted, but the one we want to point you towards, if you want to know more about Junior, the experiment we're going to be seeing today, is Craig's Junior paper. There will hopefully be a link sent into the chat soon. Well, you can go ahead and look at that. The title, I did not write down the title.
That's right. We'll figure that out and we'll come back to it in the not too distant future.
Exactly, yeah.
But yes, there's
There is
info
that.
out there.
Yep.
Other than just looking at the donut and being like, whoa, crazy.
Yeah, that's about the design and sort of overview of the Junior experiment.
Cool. And so we're at T minus 1 minute. Does this, again, I'll ask again, does this mean we should be tuning into the control room? Let's see. See what they're saying.
They are still waiting for the magnet to cool down, so they will not.
Nothing.
Yeah.
Nothing. They're always saying nothing. It's only a matter of time. Cool. Okay, sweet. So, again, here we are. OpenStar Plasma Showcase live stream. You're about to see the culmination of 4 years worth of work from a very dedicated team of engineers, physicists, as well as everyone else who makes the company run, right? We're about 70-ish people. There's been a few more that have come through the doors, and so this is a very big moment for everyone on board. And
So-
you'll see the morale's high.
Yes. We should do some round of introductions for the control room while we're here. So we've got about 30 seconds until we're scheduled to start the undocking procedure. We'll start hearing some comms then. But for now, we can introduce the voices that you'll be hearing. So the main one is Eleanor, our experiment operator. She'll be leading the sort of overall task sheet and keeping everybody on track. You'll also be hearing...
She's the one on the far right of the screen.
far right of the screen. And then you'll also be hearing Ryan, who's on the far left of your screen. He's the docking responsible engineer. We'll also introduce our dockers. So there will be 3 people down in the chamber when we're docking. So it'll be sort of zoomed in like this. These will be
Emily?
Emily?
Yep.
Yes. Sorry, I was just switching over some cameras. Emily, Mike, and Theo. Emily was actually the person that designed the chamber and brought it in through the roof and organised all of that. You'll see that...
There she is there, actually.
Yeah, there
with
she
the
is.
Green hat,
Yes.
safety hat on.
Yep, that's Emily. You'll see her close up in the docking chamber when they enter.
Yep, and we also got Mike. He's been with us for a good amount of time. Mike Buchanan. He's one of our mechanical engineers, and has been here. He might have been in the first sort of 10 or so.
Yeah, he was. Yeah.
Yep. So he's been around for a long time and has done a lot of work on the stocking system, on the vacuum vessel, all sorts of parts.
Yes.
Right.
And then Theo joined us more recently, but has been doing some great work on the cryogenic slush system that we're designing for cooling our future magnets. And we're getting some comms in now. So we should actually, now that we've started, we can bring in the comms.
Here we go.
Mike? Mike?
Mic check.
Confirm.
There's some good mic check etiquette there from the team. Getting prepared. Cool. So Eleanor's going to be driving us through the task sheet for this part of, for most of the experiment. And as we said before, Ryan on the far left is the the responsible docking engineer. And so you'll hear him sort of responding to a lot of what Eleanor's asking for and giving her the numbers, giving her the data, and making sure that everything is as it should be.
Yes. Cool. So we've just got confirmation that it now is beginning to start the undocking procedure. What are we expecting to see out of the undocking procedure? I think that is something that people might ask.
Yeah, very useful.
So essentially, we have in front of us, we're actually looking at the docking screen right now, two main bayonets with lots of pipes going towards them. Those bayonets are currently inserted inside the core magnet. They are pumping around a bunch of high pressure helium gas that's been cooled to around 20 Kelvin or below, and that is currently being used to cool the magnet. We don't want those. We want to extract those, and that's the main part of the undocking procedure, and why we sort of called that T equals 0. We just got confirmation that pre-call is complete, so we can actually start the undocking procedure in earnest now. We can leave you to the control room, and we'll come back to you with more facts later.
603. Required equipment, docking tool set. Done. Starting criteria, 404 plasma prep complete. Confirm. 405 radiation safety sweep complete. Confirm. 307 complete charging and pre-cool core magnet complete. Confirm. 803 prepare top magnet for levitation complete. Confirm. Control room populated with all required REs. Confirm. Fuel purge valve and fuel control valve are closed. Confirm. Core magnet current, 710 amps. Cryofan inlet temperature,
27 Kelvin.
27 Kelvin. Flux pump primary temperature,
58 Kelvin.
58 Kelvin. Flux pump electromagnet temperature,
58 Kelvin.
58 Kelvin. Core magnet maximum coil temp,
25.5 Kelvin.
25.5 Kelvin.
Thank you.
I have a hold point here, Svonko. Are we all good to continue on?
Yes, we are.
Great. Okay. 1. Stop cooling core magnet. Manual docking operator take ECRH lotto key from safe.
Confirm.
Electronics. Check electronics temperatures are above 40 degrees Celsius.
We're at 37, 39 and 40. That's close enough. Confirm.
Thank you. Operator, docking enter test cell. Just check you don't have anything in your pockets that you shouldn't have.
No.
Cryofan off and timekeeper start timer. Just double checking, Svonko, we're good to do this? Yep.
Yes, we are.
Okay. Confirm cryofan off. 2. Isolate core magnet lines. Manual close cold box cold isolation.
Stand by. Confirm cold isolation closed.
Cool. So we just heard that the cryofan was just turned off. That was the key step that actually stops cooling for the core magnet. So now nothing is not being cooled. We're now, this is when the true time pressure starts. We need to do all the things we want to do before the magnet warms up and far enough that it actually starts to quench and do bad things.
So we're on the clock. Relatively long clock.
Yeah, relatively long clock, to be fair. We'll see it. Hopefully it'll be done well before the 2-hour limit, or 90-minute or 2-hour limit that we have this thing can levitate for. Cool. Anyway, we'll pass you back to the control room.
Confirm closed. Cold box turbo pump motor off. Confirm off. Operator, close cold box turbo backing isolation. Confirm closed. Operator, open cold box roughing isolation. Confirm open. Manual, slowly open helium ambient vent until helium is vented.
Stand by. Opening now.
9.2 bar, coming down. 9 bar. As expected. 8 bar. 7 bar. 6 bar. 5 bar. 4 bar.
So right now they are venting the helium from the cooling lines. The next stage will be to actually pull a vacuum on the cooling lines so that we can fully remove them without puffing a bunch of helium into the chamber.
Oh, yeah.
Yeah.
That's the dream, not doing that.
Not doing that. That's the dream.
1.8. 1.7. 1.6. 1.5. And close now.
Closing. Confirm ambient vent is closed.
Manual and docking, slowly open vacuum purge.
Stand by. Opening now.
Confirm pressures are spiking.
Recovering.
We're still going up. We're at about 60, 80 millibar. Plateauing. Peak at 120. And starting to come down now.
Okay, open it all the way. Confirm vacuum purge is open.
Thank you.
Manual, confirm all helium valves are fully seated.
Confirm.
4, prepare cold box and retract RTL. Operator, close cryostat valve. Confirm closed. Close cryopump gate valve for chamber. Status in transit. Confirm closed. Operator, close turbopump gate valve for chamber. Confirm closed. Manual, confirm open docking manifold isolation.
Confirm.
Manual, retract transfer line A and lock in place.
Take it nice and slow.
Cool. So the eagle-eyed viewers might have noticed that we've just closed the cryopump gate valve. So it's the big void circle that you saw behind the central shaft on the bottom left corner of your screen. This is just to make sure that we do not end up saturating our cryopump. Essentially, the cryopump works by freezing gas onto it to remove it from the vacuum chamber, and we don't want to freeze too much stuff onto it before we actually want to keep pumping gas out of the chamber.
Yeah, cryopump's quite
Yeah.
what's the word? liable to
Yes.
break.
Yeah. Anyway, we'll return you to the comm so you can hear them talk about retracting the bayonets from the magnet.
Nice. A retracted, confirmed. Nice work.
Manual, retract transfer line B and lock in place.
B retracted, confirmed.
Operator, turn off heater control, cold and hot side.
Sorry, Eleanor, can you repeat?
Operator, turn off heater control, cold and hot side.
Cold box pressure is recovered to 1 millibar, still coming down.
Thanks, Ryan. Confirm heater control, cold and hot side off. Docking, wait until cold box vacuum pressure drops under to E negative 1 millibar.
Yep, we'll have to wait here for a couple minutes. Cool. We're currently at 8 E negative 1. Pressure is coming down in the vac locks now as well. We are at 5 E negative 1 in the cold box.
So just a reminder, they are waiting for the helium to be pumped out of the vacuum jackets and the helium transfer lines, so we don't end up puffing into the chamber.
Vac lock pressure is now acceptable. Cold box still coming down. Cold box pressure 2 E negative 1 confirmed. We're good to move on.
Manual, close vacuum purge.
Vacuum purge closed, confirmed.
Operator, open cold box turbo backing isolation. Confirm open. Operator, cold box turbo pump motor on. Confirm on. 5, helium top up if required.
Helium top up not required.
Great. Skipping to step 6. Retract vac locks. Docking, wait for docking manifold pressure to return to less than 5 E negative 1 millibar.
2 E negative 1, good to move on.
Manual, close the dock gate valves A and B and lock in position.
A closed, confirmed.
Confirm B is closed.
Operator, turn off ion gauge for chamber.
Confirm, I see ion gauge off.
I think my screen's just not responding. Okay, thanks Ryan. Manual, retract backlock A and lock in place.
Oh. That's beautiful.
A retracted, confirmed.
Manual, retract backlock B and lock in place.
B retracted, confirmed.
7, disconnect e-dock. Electronics, run undock command.
Chamber burps are good.
Repeat that, Ryan, sorry.
Burp is good.
Commander's run.
Thanks, Joe. Electronics, turn off electronic heaters PSU output.
So we just heard that they are now going to undock the e-dock, or remove the e-dock from the core magnet. This is the main, source of data from the core magnet. And this is sort of, after this, we're now completely blind. We have an IR link set up between the magnet and the chamber, but however, as you'll see in a bit, the magnet does spin, so we don't really get that much data from it. So now, after this is done, magnet will be totally blind, and we're just running on time. And we've done this enough now that we know exactly how long we can sort of disconnect the magnet for before everything gets too hot.
I enjoyed Emily's exclamation of beautiful when that retracted easily.
Yes.
It's genuinely what engineers find beautiful.
Exactly.
Docking, wait for turbo pump to reach full speed.
Confirm turbo full speed.
Operator, close cold box roughing isolation. Confirm closed. Docking, ensure cold box vacuum pressure holds stable.
As a quick response to some of the questions in the chat, also, it's worth saying, I think we're approximately half an hour away from the plasma shots occurring.
Yes, that's right.
We've still got, the undocking and the actual levitating of the magnet itself. To be fair, watching the levitation part happen is also quite exciting. So I wouldn't recommend missing that.
Yep.
And that'll be, I don't know, plasma in half an hour.
Yep.
Let's say 20 minutes before that or something along those lines.
Yeah.
Stand by. ECR switch to on.
Was that if it confirmed
Yes,
you?
confirmed.
Sorry, thanks. Manual, open helium fuel supply ball valve and helium fuel bottle isolation valve.
Confirm both.
Docking, confirm chamber vacuum pressure less than 2 E negative 1 millibar.
Confirm chamber pressure E negative 5.
Operator, open turbo pump gate valve for chamber. Confirm open. Operator, open cryo pump gate valve for chamber. Confirm open. Docking, confirm chamber pressure, vacuum pressure less than 1 E negative 4 millibar.
Confirm E negative 6.
Operator, turn on ion gauge for chamber. Confirm on. Levitation, confirm load cell reads 0 kgs.
Confirm.
Confirm launcher position is approximately negative 975 millimeters.
We're about 10 mil off, I believe.
If not, press set to turntable position.
Yep, confirm.
Cool.
Manual, align IR.
It's about time we start introducing some more people. So the new voice you just heard was Emerson Swanson Dobbs, levitation operator. He is being assisted by Josh, who's going to be the responsible engineer for the levitation system.
Mm-hmm.
We've just finished the undocking procedure, so we'll be hopefully levitating very soon. We'll also have a few more introductions. We've got Rod, who's going to be the responsible engineer for the top magnet. And
so Rod is on the right of that middle
right
desk.
of the screen. We also have Craig, who's going to be our physics operator for the plasmas.
Mm-hmm. Next to Rod. Oh,
next to Rod.
Well, just did a little wave.
Yeah.
Is he waving at us?
I think so.
How did they know?
And then we've also got Darren, who will be our session lead. He's on the left of the middle row, and he'll be doing more of the commentary while we've got plasmas and levitation going.
Mm-hmm. Mm-hmm.
Cool. So, soon we'll hear from our CEO Ratu, right before we move on to actually levitating the magnet.
Okay, very good. That's something to look forward to.
Yes.
Cool. How long have we got until that happens?
About 5 minutes.
Cool. Very good. Stay tuned.
Okay, we will continue on until the hold point in the task sheet. Great, okay. Starting task sheet 407, levitation and plasma shots. Required equipment, session plan ID 007.
Confirm.
Starting criteria 404 plasma prep complete. Confirm. 405 radiation safety sweep complete. Confirm. 603 stop cooling and undock complete. Confirm. Security camera pointing at magnetron. Confirm. Top magnet highest coil temp
19.5 Kelvin.
19.5 Kelvin.
Cool.
Alrighty, so before we hit the levitation procedure, we might as well answer some of the questions that we got in the chat. So in particular, we've got one here saying, how long will you have plasma? And that is a very good question, which answers to actually tell you a lot about what's going on, right?
Yeah. So essentially, we will be having our plasmas today will be approximately 20 seconds in length, depending on what Craig and Darren decided will be a good length of shot. Then we will do between 2 or 3 of those shots today, just to give everybody a taste of what these plasmas look like and sort of get the excitement going.
Mm-hmm.
However, there is no limit to how long we can run these plasmas for. Theoretically, we could just turn on the microwaves and walk away and come back a few hours later, it'll still be there.
Mm-hmm.
If we wanted to run the microwaves the entire time, we could. We could have the plasma running for an hour or two.
Yeah.
That'd be fine.
So it's worth when you hear a lot of sort of news about fusion devices that are able to sustain a plasma for a certain amount of time.
Mm-hmm.
The things that are reported kind of depend on the design of the machine,
Yes.
right? So a tokamak, again, we'll go back to the analogy of trying to squeeze jelly with your fingers. It wants to pop out. Because it has these instabilities, it means that it is a lot tougher to keep it stable in that configuration that's needed. And so when they talk about having a particularly sort of like a 100-second plasma or something along these lines, that's because that is the parameter that makes the most difference to how successful they are with the machine that they've built. Whereas our design is different. It's got more of this quasi-stability, which means that we're sort of less focused in on how long we can keep it the plasma stable for, and we're more focused on how long we can actually keep the whole thing levitated for, right?
Yes.
That's more of our sort of parameter.
Yeah.
And that all comes down to the sort of cryogenics, etc.
Exactly. Yeah. And then so once again, this one is just cooled by helium, and then we just use what's called specific heat of the core magnet. So the energy storage is in the temperature change of the core magnet in order to keep it levitating. Future magnets will use latent heat. So we'll use a cryogen slush that will be either neon or hydrogen, depending on which one we want to use. And then we will use that to essentially store the heat on board without changing the temperature of the magnet. And that gives us great advantages. If we want to dock it really quickly, we don't have to wait for the entire thing to cool down. We can just pump out a bunch of liquid and it will be, super short dock time.
Another question we have is, what is the scale-size of the device at the side view? So we probably talked about that right at the start of the broadcast, but worth reiterating this.
This is the scale.
Yes.
So essentially, our magnet is 1.2 meters in diameter. The chamber is 5.2 meters in diameter, and we have some people in here for scale. So for when we're watching the side view, this is sort of what you should keep in mind when watching that. Cool. They're lifting the core magnet. We will switch to this view.
There it goes.
Yes, David.
We're locked in now.
So soon we will see the magnets get in range of the laser position sensors. This will be coming up on the core magnet position plot on the bottom left. We have 4 lasers pointing at the magnet from different positions to measure its height, and we're sort of plotting the average of that here. So hopefully when we get close to the proper levitation position, we'll start getting a reading from those. We have about 30 millimeters of travel or sensing range on those lasers, and that's all we really need to levitate it. So the accuracy that we're going for is around about 0.1 millimeters for the levitation control scheme.
And that's enough for us to be confident in its position.
Exactly.
To the degree that we need it.
Yeah.
Right?
If we get out of that range, we will just drop the magnet. That was safer that way.
Cool. Cool. So we can see there that the position of the core magnet is now visible on our bottom left plot. What is 0 in this position plot? It's arbitrary, right?
It's arbitrary. It's sort of like the 0 position. We want 0 to be in the center of the chamber. That's sort of where we want it to be. We'll probably be operating plus or minus 1 millimeters around that, just to essentially give us some room, depending on how the control team decide how much space they need to actually run the control system.
Cool. And I guess next up is turning on the top magnet current so that we can hold it in place, right?
Exactly.
Cool. So we expect to see this other graph turn from noise into something specific.
Yes.
Yep.
Confirm lasers read minus 13 millimeters plus or minus 2 millimeters.
Confirm we're at minus 14.1 millimeters.
And hold here.
We are about 5 to 7 minutes ahead, so just wait for the speeches.
Thanks, Marco.
Cool. So it seems like we've paused proceedings to wait for the speeches and for all of our guests on site to arrive in and take their seats. So.
Cool. Very good. How many people? We got something like 80 people turning up.
Yeah, 80 people turning up, yeah.
Which is very cool. And again, reiterating that this is a really big moment for all of the work that the people have put into building this machine over the last 4 years. So we've kind of gone and told everyone, hey, come check this out because this is going to be pretty cool. Nice. Ears Made Easy said, I'm very much enjoying this coverage. Would be happy to put my name on a future list. Do we have you can sign up for the newsletter, right?
Yeah.
That would be a reasonable place to start. Where do we go for that? Just on the website, surely.
Yeah, I think so, yeah.
Might as well plug all the things on the website, yes. Like if any of this has piqued your interest, we also have an expression of interest open on all the time.
Yep.
Obviously building a fusion energy device requires a lot of talented people, and we're only going to need more and more, particularly as we go to build Tahi, our next generation machine.
Yep.
So, and again, you're talking to the right guy. So you never know. So yeah, on the website, openstar.tech, go on there, you can sign up for the newsletter. Expression of interest is on there as well as a little bit about, obviously, who we are and what we're trying to do. Have we introduced Zvonko? There's also Zvonko.
We have actually forgotten Zvonko.
Yeah, so you would have seen a guy being really quite animated. He's at the bottom of the screen there. That is Zvonko. He's one of our principal engineers, and he is the experiment manager for this whole experiment, which means he is the one poking and prodding everyone to turn up at the right time to do the right thing, getting all our task sheets. As you mentioned in the chat, this is a relatively intricate way to start up a machine.
Yes.
It requires a lot of coordination, and Zvonko is the guy that is doing that for us there. Very talented magnet engineer, previously HTS 110.
He was previously HTS 110, that's right.
So again, it all links in to the NZ superconducting ecosystem. What good people. Okay. What's going on now? We're still paused? Let's check in.
Yeah, we're still paused.
Cool. Okay, so after our speeches that we have, we're going to see like the core magnet turn on and fix, the top magnet turn on and fix the core magnet in place, and then a retraction of particularly this bottom actuator that you can see here, right?
Yeah, so essentially underneath the core magnet we have a cone. Looks very similar to the cone on top. That's currently holding the core magnet in place while we wait for the top magnet to be turned on. Once again, we're just waiting for guests to arrive on site and get seated. This is all part of the plan. It's also part of the reason why we're only getting 3 plasma shots today, is we need to allow for lots of time for people to get in and out of the building and go about their sort of schedules.
Yeah, very good. And we've got another. So Bruce Hickman asked, how many times have you done this exercise to date successfully? So like this is, again, in Halloween last year, we had our first ordered plasma, which means that we were holding it in place and we were able to produce a plasma. But obviously that's not ideal. It still has all the things in the way, like when the plasma can hit things, etc. We need to have it levitated in order for this to be a proper proof of concept. We've done practice runs, but really this is the first time we're putting this out into the world. No one else has seen any footage of this happening before, and this is the place to see it. So this is right on the edge of new.
Yeah.
Obviously, we've put a lot of work into making sure that it will definitely work.
Yeah. For context, we have run this type of experiment with the levitation and plasma, I think 3 or 4 times before today, to make sure everything's working, get some data out of it. Because we were excited to actually start doing some physics using these new system that we have. But yes, today is more about the showcase and the work that we've all put into designing and making this honestly really cool machine.
And I mean, immediately on the other side of this, right, is as Tom just kind of alluded to, doing some physics, right? So this has been a huge amount of engineering, and there's a few frontiers in what needs to be done for producing a fusion energy device, and one of the really important parts is the plasma physics, right? Yeah. And plasma physics is very, very complicated, many energy scales, different models that can be used to attempt to simulate what you believe is going to happen. Oh,
cool. We're going to switch over to Ratu's speech now.
I have pressed the button. It is working, just not for you. Welcome to OpenStar. My name is Ratu Matata. I'm the founder and CEO. Thank you for coming and joining us for this event. This speech is not a speech, it's just a series of bullet points. So this is about as casual as it's going to get. Like any event, we're going to start off with housekeeping and health and safety. In the event of an earthquake, drop and cover. You have chairs. Try to fit underneath one. In the event that we need to evacuate in an emergency, we can go through the entrance that you have all already been through. If you go down into the workshop, there are also exits out past the experiment, and there is also an escape path just around on the other side of this TV through that door. All right, that's our housekeeping out of the way. What you're about to see is the culmination of, I think, about 4 years of hard work for about 65 people to pull together a machine that basically people thought was impossible. What we're about to do is take a half-ton superconducting magnet, cryo-cooled, and then we're going to float it, and then we're going to put a plasma around it. Now, those are just a bunch of words, and we wanted to put a lot of effort to bring you all together so you could actually experience what this is like. In different forms and different iterations, the team here at OpenStar have been running these experiments, experiencing what this is like. This is actually normally our office. It's normally full of people's desks and computers, and we'll run an experiment like this and people will just be sitting there trying to do work while they actually watch the live stream, and we burn 3 hours of productivity. But tonight we're putting in the effort to try take you through this journey as best we can. And rather than me ramble about it, I'm actually going to hand you over to Darren, our Chief Science Officer, who is by far the world's most experienced person at running levitated dipoles.
Thanks, Ratu. Yeah, I'm the Chief Science Officer, but tonight I'm actually Session Leader, which means that all I basically do is make 2 decisions. So that means I get to tell you what we're about to do. So I'm going to take you through step by step. We're now at step 3 of our system, and that's basically where we start to energize the magnet. And if you look at the picture, hopefully it'll be showing soon on the side view. Above the core magnet in the center of the machine, you'll see the core magnet, and that's that half-ton magnet. It has about 1.5 million ampere turns of current in it, and right now it's sitting on a cone that looks very similar to the cone that you see above. So it's just sitting there. What we're going to do at first is there's another magnet just on top of the machine that you can't see, and we're going to pick up the weight. So what we'll do first is just ramp up the current on that top magnet and pick up the weight. So that half ton will then become about 100 kilograms. And so that's the first step.
Click Start Run to begin an MDS Plus run.
Confirm.
Under Levitation System Actions, click On.
Confirm.
Set target current to 10 amps and click Set Target.
Target current is 10 amps. Setting target. We're ramping current up.
Ensure that the weight reported by the load cell decreases.
Stand by. Confirm the 10 kilos of the core magnet weight has been taken up by the top magnet.
Step 4, energize top magnet. Levitation, set the current ramp rate to 25 amps per second.
Confirm.
Ramp top magnet current to 400 amps.
Confirm top magnet current target set to 400 amps. Moving to target now. Ramping up. (200 amps).
As you can see here, as we're ramping up the top magnet, we can also see the position of the magnet increase as well, and that's because we are literally lifting it up as we speak. And also the lifter catcher acts as a bunch of springs, and we are sort of unloading those springs as we are increasing the magnet, the current in the top magnet.
So they're sort of describing like a weight that has been felt.
Yes.
On that sort of bottom support.
Yep.
And so as they lift it up, that weight will go down.
Yeah, at the top left of your screens, you can see the current measured weight of the core magnet. You can see it's actually quite low. It started at about 570 kilograms, and now it's sitting at about 80, which means they're about to go for levitation.
Cool.
Everybody done Russia. Targeting 480 amps. Confirm we're at 480 amps.
Levitation RE, give launch Z target.
Sweet. So yeah, 70 kilos, so good to launch. We'll launch from target 0 millimeters.
Setting the target to 0 millimeters.
And then we have a hold point here.
Okay, so we've now got
90% of the mass.
Levitated, but it's still sitting on the bottom, just a little bit. What's going to happen next is we're going to pick it all the way up. You might have tried this when you were young or maybe recently. Take two magnets and you take one above the other one, try to levitate it. What happens? It always goes up or down. It never sits there stably. So what we do actually is we have these lasers that look at the top of the magnet. And there's 4 lasers around the look at the top. You can't see them there, but they're right there. And what we'll do is we'll have a feedback system that will look at those lasers 4,000 times a second and adjust the current above. So what happens next is actually we're going to transition the control system to flight mode. And that basically is turning on that feedback circuit. And of course, we don't want to yeet this thing into the top cone there. So this is actually for the levitation control operators right now. This is the exciting part. You're going to see it move just a little bit, though.
Okay, step 5, transition to flight mode. Operator, turn off vacuum chamber ion gauge. Confirm off. Close turbopump gate valve for chamber. Confirm closed. Close cryopump gate valve for chamber. In transit. Confirm closed. Ensure the MDS plus gate valve control is set to false. Confirm. Top magnet, confirm, go, no go for launch.
Confirm, go, let her win.
Levitation RE, confirm, go, no for launch.
Confirm.
Levitation, go to flight mode.
Confirm, I'll count us down and then go to flight mode. 5, 4, 3, 2, 1, launch. Launch looks good. We're tracking the Z target. Looks good.
Okay, so that's actually a successful launch. It is still sitting just a tiny bit on that lifter from below. So what we're going to do now is very slowly bring that lifter down, and you'll see that we'll go into levitation.
Okay, 6, prepare lifter separation. Levitation, move the core magnet to +2 millimeters.
Confirm setting the core magnet Z target to 2 millimeters and moving to target. Confirm we're at 2 millimeters.
Move the lifter down to -13 millimeters using move to target slowly.
Setting the lifter target position to -13 millimeters and moving to target slowly. Moving down. -5. -10. Confirm lifter in position at -13 millimeters.
Confirm levitation achieved.
Confirm I see free rotation of the core magnet. We have achieved levitation.
Levitation RE, confirm go, no go for full flight.
Go.
Okay, and then we have another hold point here.
Okay, so what you just saw there, and if you look very carefully, you might not have seen it, but it's actually very slowly rotating around. And that's a clear indication that we're inside of a vacuum chamber with 1/1000th of an atmosphere in there, and there's going to be no there's no friction there. So what happens is we have a little tiny bit of unbalance, and it'll just sit there and rotate back and forth for hours at a time because there's nothing to slow it down. Clear indication we have full levitation. Now this would be a good time for our while we wait for our guest here. We have 5 minutes. Okay. So the next step that we would be talking about is we will lower the entire lifter and then get ready for our first plasma. But we can wait for our guest to show up. Move on to the next step.
Yeah.
Yeah, it would be a good, like this is actually a nice place to wait because it's actually fully levitated. It's also fully safe, so if anything weird happens, it'll be happy there. If there's any questions, we would love to answer any questions of what you were seeing. I can also give some interesting facts of what's going on. I mean, what you see there is, I mean, it is half a ton. I mean, it's an amazing sight. This is the basically the largest dipole magnet that's been levitated for dipoles. It's actually a little bit bigger than LDX's, which was at MIT. And prior, there was also another large one, relatively large, but half size, RT1. It's actually still operational at University of Tokyo. Yeah.
Do you mind just explaining what we're seeing on the screen? I can go starting from the bottom going up, if you don't mind. So you've got the gray area.
Yeah. So what you're so it's right. I mean, it's a little hard without the sort of three-dimensional picture. What we're looking at is inside of this. If you looked as you came in, or maybe you've seen the other pictures, it looks like a spaceship, right? So it's a big ellipsoidal vacuum chamber. And so you're looking mostly. You're seeing in the background there is the bottom part of that dish, and then there's a cylinder going up, and then another dish on the top. And so that's the background. What you see in the center column is our like sort of lifting mechanism, and at the top there is another cone, and that is a catching mechanism. Suppose we were to yeet it to the ceiling, this could cause quite a bit of damage to the magnet. In fact, even to the vacuum vessel. So what that is actually a very clever engineered piece that actually will crush if we were to go up and actually do it safely, so that the magnet will only see less than, I think, about 5 Gs, if I'm correct, on the specification for that. And then the little bit that you see at the very bottom is another cone just underneath the coil, and that will actually come out. As I will explain, I mean, as we'll see, is those cones there, they're there to basically limit the motion of the coil should we lose control. But the important thing is that those cones, when we get them into full flight, are outside of the plasma region. What we're trying to do in a levitated dipole, and the reason we call it a levitated dipole, is this device is inspired by nature. We are making on Earth sort of a mini Earth. So the Earth's magnetosphere is a great particle trap. It's the reason we have life, right? The solar wind comes in; it would really ruin life if it was constantly barraging us with these ions, and so it traps those particles. But it's not a perfect trap. We lose some of those particles along field lines into the poles, and this is the aurora that we know. For a fusion, we want to confine things really, really well. So we're doing nature one better here by levitation. What we're doing is we're getting rid of the losses, those aurora, into the poles, and by levitating and by moving away all supports, that plasma now can go all the way around the coil and not be lost. And the plasma itself is really well confined by magnetic fields. It moves about 1,000 times faster along the magnetic field than it is across. So this is one configuration that really can confine very well the plasmas.
What are the dimensions of the plasma?
So the vacuum chamber itself is just over 5 meters, 5.3 meters in diameter. So basically the plasma will go nearly to the center, nearly to the edge. And I think it's around 40 cubic meters of volume. Of the plasma? That's a really interesting question. So of course, what we've done here is made a vacuum. So we've made it at about 1 billionth of an atmosphere. Before we make the plasma, we're going to puff in a little bit of gas. How much little? It's about 15 micrograms of helium. But we're going to heat it up to about 1 million degrees. Yes. Yeah, are we good?
Cool. Okay. So Darren went through a few of the things that we can see there. In particular, I think the main thing to point out, again, for maybe people who've just turned up, is you can very slightly see that the donut, which remember is about 500 kilos, is very slowly rotating. It wouldn't really do that if it was stuck on anything.
Yeah.
But we can expect in the not too distant future to actually see that support retracted, and it will become a lot more obvious.
Yes.
And a lot more clearly levitated. But it is levitating now, and if you keep track of one of those sort of black dots that you can see, they are moving very slowly. Should we tune back into Darren?
Yeah, we should.
Self-similar plasma, very peaked, very interesting. This would be great for fusion. But he's sort of a theorist. He's really a great theorist, and very well known. In fact, he's actually responsible for fiber optics today as we know them. But he inspired MIT and Columbia to get together and build the first experiment, LDX, to actually test that magnetospheric space physics in a laboratory. Quite a different parameters, right? I mean, you're going from things that are bigger than planets down to something, as you see, on a planet. And so we did that on LDX, showed that it really worked. And here at OpenStar, we're going to take the next step. We're going to show that we can take it from a laboratory experiment, which really shows good confinement, to actually proving it out to we're going to make fusion with this and get it to the points where we can actually make fusion. So that's the next step we're doing here. Okay. So our guests are about to come upstairs, I think. Yeah, here they come.
Cool. So I think it's probably worth pointing out that the guest that's just arriving is Christopher Luxon, the Prime Minister of New Zealand. How good. That's why we're waiting.
Yes, that is why we're waiting.
We will drop it, but we're not quite ready for you to press the button yet. Yeah. So to catch you up, Mr. Prime Minister, we are actually levitating right now. If you look at the screen, or you can see this one here or the one over there, the core magnet is levitating, but only by about 13 millimeters above a catcher. So it's slowly rotating there. We're about to drop down the lower launcher so it gets into full flight and make room for the full plasma to be created. So, and that's the last sort of scary bit, and then we can remove. Yeah. Okay. So let's get on with removing the lifter from the plasma region.
Move the lifter down using move to free flight position.
Confirm moving to free flight position. Lifter's moving down. Halfway there. Confirm lifter is in free flight position.
Set Z target to -1 millimeter, the nominal levitation height.
Setting the core magnet Z target to -1 millimeter and moving to target. Moving down. Confirm in position.
8. Prepare for plasmas. Docking. Confirm go/no go on vacuum pressure to open gate valves. Operator, open the turbo pump gate valve. Confirm open. Open cryopump gate valve. In transit. Confirm open. Turn on ion gauge. Confirm on. Open fuel control valve. Confirm open. Set MDS plus gate valve control to on. Confirm on. Confirm radiation warning lights on. Confirm.
While they are prepping everything for plasma, we can just briefly go over why the core magnet is rotating. So actually, this is because center of lift or center of force is it's gone now, is not the same as center of mass. That's mainly because we have a bunch of iron. So we have a bunch of iron sitting on one side of the magnet to protect the flux pump as much as, or the HTS power supply as much as possible, and that's causing it to be pushed down slightly, which is causing the magnet to tilt and then rotate back and forth.
Okay.
Yeah. Anyway, we'll go back to Darren and continue with the shot cycle.
There is one thing we do have to actually initialize it all. So would you do us the honor of actually pressing that button?
Is it a big red button or is it?
Please, no. So let's be clear. There's a red button, a yellow button, and a green button. Just press the green button.
Just the green button. Okay.
But I'll leave you with Eleanor. She'll take you through the steps.
All right, Eleanor, I'm in your hands. Yep.
Hello. Okay. We can do a practice press at the moment. Basically, how it works is
Emerson, nice to meet you.
So I will arm it by turning this key. So you can press it right now and nothing will happen. So like. Easy peasy. You can give that a go if you want to test it out.
You want me to test my pressing skills? Yeah.
Great. Perfect. So what we're going to do is I'm going to confirm with all the responsible engineers that everyone's ready for the shot, and I will count us down. I'll go.
And that shot is going to do.
What it's going to do is it's going to turn on all the systems, so there'll be about a 10-second delay, and then we will see the plasma, so we can watch it on the screen up here. And so what I'll do is I'll turn the key and I'll go 3, 2, 1, pulse. And on pulse, you'll press the button. Yeah, exactly. So there's a few things we need to do first, but then that's how it's going to work. Cool.
That's great.
Yeah. There's about 30 seconds of stuff we have to do, and then Eleanor will take you through the last bit.
Good. Press on pulse.
Exactly. Cool. 9, begin plasma shot cycle. Session leader and physics, set up MDS plus shot.
I'm writing shot alpha to the tree. Ready for a net.
Physics, ensure chamber pressure is less than 1 E-6 millibar.
Confirm.
Levitation RE, go, no go for closing gate valves.
Yeah, go.
Physics, when ready, initialize shot.
Initializing shot 001. Initialization complete.
Confirm turbo gate is closed. Confirm cryopump gate is closed. All operators prepare for shot.
Ready. Ready.
Okay. 3, 2, 1, pulse.
Helium good. Power on. Woo!
Yeah, that whole section came with the We have the microwave heating power source.
Now it's forward plasma the whole cylinder.
So
shot complete.
I kind of think that might have been beginner's luck. You want to go for another?
You want me to do another one?
Yeah,
well, I've got really good. I mean, I can try like, yeah, this whole, yeah, I could come back and be your assistant.
Yeah. It'll take us about a minute or so to have everything cycle through and basically pump out the old gas and get ready for the new gas. So just another minute or so.
Yep.
Confirm the turbo gate and cryopump gate valves are open and shot cycle complete.
Bravo.
So physics go, no go for next shot.
Just give a few more seconds on the pumping. In the meantime, I'm going to load shot Bravo into the tree. Okay, we are below 10 to the minus 6 millibar. We're good to go for the next shot. I'm ready for a net.
Please run a net when ready.
Right, initializing shot 002. Initialization complete.
Confirm turbo gate closed. Confirm cryo gate closed. Okay, all operators prepare for shot.
Ready. Ready.
Okay. 3, 2, 1, pulse.
Helium good. Power on.
And shot complete.
Running store.
Okay, thank you guys. This is our plasmas for today. We are about to basically we'll stop levitation now and put the machine safely to bed. This will take us a little bit to do, about 5 minutes. So I'm going to leave you with Ratu, our CEO.
Thank you, Darren. And thank you, Prime Minister, for pushing the button. I'll let you in on a little secret. I've actually never pushed the button. My team just assumed that I'm too much of a interruption to let me intercede into the carefully managed task sheets. So, to be really clear on what we've just seen, to put it into context, our industry thought that was impossible. In particular, being able to build a magnet like the one in that chamber and have it be disconnected from all of the support services that a magnet normally needs, and then be able to levitate, right, half a ton, just to, and we've done this a little bit now, and we're still a little nervous when we pull away that catcher, right? And to be very clear, if the Prime Minister had pushed the red button, that would have actually dropped the magnet. That is what the system is designed to do. In what we would call a controlled catch, where kind of we have to turn everything off and get things under control. But everything goes according to plan. These systems are absolutely engineerable, buildable, operable, and our ability to develop this stuff fast is just world class. And so I'm actually distracting you all because we're actually going to go downstairs and do a few proper speeches that are actually rehearsed. But we have a very loud generator outside, which makes giving speeches outside a little bit difficult. And am I filling up my 5 minutes appropriately, team? How's the generator? Is it off yet? Man, what am I filling time for? Oh, my Lord. Now, you've had a chance to ask questions of Darren. But I'm also more than happy to answer questions. You can ask the same questions and see if I can answer them as well. Sure.
Can you explain to us how hot that plasma gets so we can all understand that?
I can say the numbers. Whether or not whether or not I understand how hot it is actually another question. So when you're building a fusion machine, you're trying to create a superheated plasma. And the reason we want to get it really, really hot is because we want the particles in that plasma to hit each other and then hit each other really, really hard until they squish together and fuse, right? That's why we call it fusion. To get it hot enough to fuse and be economic, you need to get to 100 million degrees. Now, this system, 100 million degrees sounds like a lot, right? Your kettle of water boils at 100 degrees without drop a million. That plasma that you just saw is already 1 million degrees. And that was done with the equivalent of 20 household microwaves. Our next machine will actually put in the amount of heating power that you need to start to go to hit those higher temperatures, right? This device was built to demonstrate a whole bunch of things, but at lower performance. So we didn't turn everything up to 11. Next time, and with the support of the government funding that we're receiving, we are going to turn everything up to 11, and we're going to get up to those hundreds of millions of degrees, or 100 million degrees.
That's what you think you will be able to deliver with the new kit?
I will let one of my 10 million degrees, and then one step after that, to get to 100. I take it step by step. And so the significance of that, like being able to levitate the magnet, get the plasma around it, obviously we need to get the plasma hot. First intuition is that if anything touches that plasma, you're going to vaporize it. And we've vaporized some stuff in this chamber already, and it's an absolute pain to clean. But the other problem is if anything touches this plasma, you just cool it down. You can't get it up to 100 million degrees, right? And so that's why levitation is at the core of what we do. It allows us to create a plasma that actually touches nothing, and without touching anything, we can actually get it hot enough to start hitting these milestones. Does that answer the question? And probably 5 others.
Nobody in the world solved that problem before, like given all the projects that are happening around the world on fusion, has no one dealt with that particular issue?
This is by far not the hottest plasma that's been made. Yeah. So proper, well-funded, like huge government-funded fusion programs around the world, they put in the amount of heating power that you need to hit those kinds of numbers. And so we're seeing fusion projects get up to that 100 million number and start to fuse. But that's really the science. The engineering question is how much money did you spend to actually get it there? How long could you keep the plasma there? We kept this plasma running for about 20 seconds. We could have done it for longer, but actually you'd all get bored and we would wonder what to do next. And so being able to get them hot enough for long enough and cheap enough. And these systems, dipoles in particular, what you see in front of you is a very economic way of pulling together the different ingredients for a fusion reactor. It looks much more, the generator's off. Cool. All right, what we're going to do is we're going to go downstairs and we're going to do proper speeches that I've practiced. Cool. Thank you much. Thank you very much, everybody.
Cool, very good.
Very good.
Great success.
Yeah, great success. That was fantastic.
And then we see the magnet being lowered back down.
Yep.
Very good. Sweet. So I guess that's everything that we expected and wanted, and good job, everybody.
Yes.
Homai te paki, as they say.
Round of applause.
Oh, plenty of handshakes going on all around. A good, strong handshake. Cool. So what do you think of that, Tom?
I thought it was great.
Yeah.
Honestly stoked that everything worked as we expected it to.
Mm-hmm.
You could see all the oscillations in the control system. You could see a really nice looking plasma.
Mm-hmm. Do you want to potentially talk a little bit about why the plasma looked like that in particular?
Oh, yeah, okay. So in terms of color or shape?
Color and shape. Oh, yeah, color.
Yeah, color. So we can talk about color first. So a normal helium plasma is purple. This one was clearly white, as you guys saw. That is unfortunate because our vacuum chamber is a little bit dirty. We got a bunch of other stuff in there when we were sort of mounting everything inside that we haven't had a chance to fully clean off yet. So essentially a bunch of random other gases outgassed into the chamber. And when we turned on the microwaves, they also got ionized and started creating their own light as well as the helium. So we got a bunch of other frequencies of light, which when you combine them all together creates a nice white light. Well, not nice, but white light. So essentially our next goal is to clean out the chamber as much as possible so we can start getting some proper, nice, pure helium plasmas. And that's when we start doing some proper science using Junior.
And by cleaning out the sort of extra impurities that are in there, that essentially means running plasma.
Yeah, that's running plasma. The plasma itself bakes off all the impurities from the walls, and as we do more of that, we bake more of it off. We start that with the vacuum pumps, and then we essentially get more and more pure helium plasmas. Yeah, so that's also worth mentioning. We did helium today. So helium is nice and cheap. It's great for just doing technical demonstrations because it's pretty similar in mass to the hydrogen isotopes that we want to actually eventually start using.
And we've got a bunch of it anyway.
Yeah, we've got a bunch of it.
Yeah.
So hydrogen plasmas are nice and pink, and then once you start going towards deuterium and tritium, they can start getting more red in color. So essentially, when you start watching, hopefully, future OpenStar streams, if you keep an eye out on the color of the plasma.
The weekly podcast?
The weekly podcast? I don't know about that, man.
No, very reasonable. Sweet. And
the shape.
Yeah, the shape.
Probably a little bit hard to talk about when it's not here. But essentially, you could actually see, if you go back and look at the plasma, the shape of the magnetic fields as they were interacting with each other. So essentially, you've got the top magnet and the core magnet interacting with each other. Cool. And I think we're going to cut to the speeches now.
Cool, very good.
We've been part of today is an economic necessity, not just a science project. While this machine has allowed us to prove the engineering of our concept, the government's support through the Regional Infrastructure Fund provides the strategic foundation for our next reactor, Tahi, to be built right here in New Zealand. This is how we answer the energy sovereignty challenge facing our nation, not by waiting to import solutions from overseas, but by owning the IP, the infrastructure, to build it right here in Aotearoa and export it to an energy-hungry world. Since starting OpenStar, people have often asked, why here? Why did the Hutt Valley of Wellington, at the bottom of the North Island, in a small country like New Zealand, put itself at the forefront of fusion research and development? Why not Silicon Valley or Boston, the United States or the UK? Why not China? My answer to this is a little bit about technology, but also what I think New Zealand is as a country. I think we are the cultural frontier, the innovators of the unexpected, not just peddlers of a new fad, but actually building on decades of vision, commitment, and actually we have Jeff Talon here, for example, who made the Hutt Valley the core of some of the best superconducting magnet engineering in the world. Make no mistake, what you saw happen today was considered impossible by our entire industry, if not for a small group of dedicated, talented, and passionate people standing atop the legacy that people like Jeff have given us. Today, that's worth an applause. Today, we are seeing a new generation of talented Kiwis staying in New Zealand and forming the critical mass to draw top-tier researchers to do this kind of work in New Zealand because it's becoming the most exciting place in the world to do it. This facility isn't just about making plasmas. It's about creating the high-value careers that allow our people to succeed, compete on the world stage, all while building and becoming part of our national fabric. Looking forward, the Regional Infrastructure Fund investment builds the specialised infrastructure that allows academic researchers, industry partners, startups, just like OpenStar, to work side by side and across borders. This is how we move from being a country that exports people, our best and brightest, and become a country that exports technology, ensuring that we develop the sovereign capability that allows us to compete in a globally diverse landscape. It is now my great pleasure to pass the floor to the Right Honourable Christopher Luxon, the Prime Minister of New Zealand.
Well, ka nui te mihi kia koutou, kia ora, good evening everyone. It is awesome to be here this evening. Can I say thank you, Ratu, for your introduction and explanation of what is happening here. For us lay people, we really do appreciate you simplifying it in the way that you have. But it's just really a big congratulations to you and to all of your team and what you have achieved and what you're contributing here with OpenStar. It's pretty special. Can I just acknowledge a few quick people? Obviously, Minister Shane Jones, he's been very instrumental in making sure we get and support this company. my good friend Chris Bishop, our boy from the hut, who's very proud to have it here as well. Under Secretary Court, it's good to have you here as well. I think Mayor's Andrew Little and Perry Z are here as well. Great to see you. And he's going to hate it, but can I just call out Kiwi icon Richie McCaw, who I was with last night, and very kindly, he got inducted into the New Zealand Sports Hall of Fame, which is quite a big deal. But actually, what you don't know about him is that he's actually a total science geek. So it's really good to see you two here, mate. Good to see you. And can I just acknowledge all the scientists and all the engineers that are here, the investors that are backing these bold ideas, the researchers and the students who actually see their future in this field, all the partners and collaborators, and of course all the families who support the long hours and the big ambitions behind breakthroughs like this. Look, one of the great privileges of this job is that you get to meet people all across this country who are doing extraordinary things across a wide range of fields and pursuits and industries. And it's not just because of the wow factor you get from seeing plasma levitating in front of your eyes after it was expertly pushed by a bald joker with a green button, but because of what we're actually looking at isn't just a scientific experiment. As Ratu said, it's very much a glimpse of what New Zealand can become if we back ourselves in advanced technology and in deep science. Throughout history, access to abundant energy has determined which nations lead and which ones fall behind. Energy powers industry, it drives productivity, it lifts living standards, and in a world that is increasingly competitive and reliant on AI, it underpins both prosperity and also our security. So we need as much safe, reliable, and affordable energy as we can possibly get. And for a government that is absolutely focused on lifting economic growth, fusion energy has enormous appeal. It has the potential to revolutionise the energy sector by providing a limitless source of safe, clean energy. And especially after what we've just seen, it is clear that this prospect is closer to reality than ever before. Huge efforts are underway all around the world to deliver meaningful breakthroughs in fusion. And there are major collaborative endeavours with many countries often working together, like the ITER project in France, which I watched a great video on the other night, and a growing number of companies worldwide pursuing their own approaches. So it is, as you said, pretty remarkable that OpenStar Technologies right here in Wellington, right here in the hut, is innovating and competing with the very best of them. It is proof that you don't need to be the biggest country to shape the biggest breakthroughs. You just need talent, you need ambition, and you have to have the courage to think differently. And the test we've had the privilege of witnessing is obviously a key step towards OpenStar's development of levitated dipole technology, a unique approach to fusion and a reflection of the ingenuity and innovation New Zealand is known for. As a government, I'm sure Minister Jones will talk to it, we are proud to be investing in OpenStar's work, and I'll let him talk more about that. But we are also wanting to reform our science sector. We want to be able to have a science system that can actually deliver more breakthroughs, more discoveries, more startups, more IPOs, and more opportunities for Kiwis to compete and succeed globally. We want, therefore, every research dollar we deliver to deliver strong results and greater commercial value than what we've been seeing. And to improve collaboration and performance, we've created new public research organisations that are focused on areas that matter most to New Zealand. And through the New Zealand Institute for Advanced Technology, we're also investing in cutting-edge work like the Future Magnetic and Materials Technologies platform. And of course, that platform, led by the Robinson Research Institute, began with a very big breakthrough in high-temperature semiconductors, superconductors back in the 1980s. And continued public investment has supported further discoveries and helped turn magnet research into real-world applications, contributing to the growth of our deep tech sector. OpenStar is part of that story. It begins with you, Dr. Ratu, your time as a PhD at the Institute, and the government's $71 million investment in this platform through the New Zealand Institute for Technology sends a very clear message that New Zealand backs its deep tech sector. Expert leadership is critical, and that's why we've also brought together a bunch of experts to actually form a funding advisory council, a research funding advisory council, to help us steer our investments towards those that have the greatest opportunities and the greatest impact. So all in all, I just want to acknowledge what a huge achievement it is and what you've all created. Fusion energy has long been viewed as a game changer, but it's also been seen as something that is perpetually decades away. And today, I think, shows that that future is beginning to take shape right here in New Zealand. And just as Ernest Rutherford actually split the atom and transformed our understanding of science more than a century ago, OpenStar is at the forefront of another scientific revolution. So can I just say to all of you, congratulations on today's achievement. Congratulations on what you're building. We need you. We want you to be successful, and we're here to back you up. And with that, I'll pass you over to Matua Shane Jones.
Kia ora tātou. Can I ask Mr. Bishop and Under Secretary to come and stand next to me, please? I'm going to pray and see if the Bishop can really float. Prime Minister, thank you for those words. Aratu, thank you for inviting us, you and your team, civic leaders, and I endorse the remarks of our Prime Minister about our great tōtara tree, Richie, here this evening. Scientists, your families, and those of you who are investors in the crowd, taking a punt on something in a distant part of the world where one wouldn't necessarily think that the breakthrough for the new frontier of energy might come from. $1.2 billion fund was created when the Prime Minister negotiated with the various leaders of ACT and New Zealand First, and Winston Peters put this into our coalition agreement. But this sum of money went to the entirety of our Cabinet. And I want to acknowledge, Prime Minister, that this was something that was embraced by all three parties. The three parties said, yes, there is risk associated with it, but if it succeeds, we want it to stay in New Zealand. We want it to be a platform where the young men and women currently thinking about careers at university, or even those who are graduates in other parts of the world, have an incentive to come back home and work at the cutting edge level of technology, energy generation, empowering and transforming our economy. So the $30-odd million, folks, whilst it's my pleasure as the steward of the fund to announce it, again, the most important thing, please leave this gathering knowing that the three parties that comprise our coalition government all support your endeavours. Your grandmother, the Renaissance leader in the late 70s and 80s for the restoration of our Māori language, will be so proud of you. She led the educational renaissance, and let's give Ratu a great round of applause. I'm told there could be something to eat and something to drink, so I'm going to allow my two colleagues to say some mercifully short words to endorse the remarks of the Prime Minister, especially the local member from the hut. No. Okay, I drink rosé. Thank you very much.
Kia ora.
Yeah.
How good.
Fantastic.
That was pretty positive all round.
Yeah.
A win for science, win for New Zealand, onwards and upwards. Ciao. No, very good. Okay, sweet. So, to everyone listening, thank you so much for tuning in.
Mm-hmm.
This has been the OpenStar Technologies Plasma Showcase live stream.
Mm-hmm.
Thanks for all your questions. Thanks for tuning in. And we've got a couple of tidbits to leave you with.
Yep. So first things first, we've got the paper we mentioned before. So we've got a paper written by the physics operator Craig. Oh, sorry, we've got another speech from Ratu.
Whoa.
Which is something that he's very famous for doing. Overseas at some place called Cambridge? Anyway. But on the topic of Rutherford, he wasn't just the first person to split the atom, he was also one of the first three people to fuse the atom as well. So this story starts with Rutherford and is going to end in New Zealand. We are the ones who are going to finish this race. Like Rutherford, we are pushing the boundaries of what's possible, but now we're doing it to actually secure the sovereign capability for New Zealand. This is more than just a machine. It's a web of people, ideas, technology, talent, drive, and passion that forms the competitive advantage that ensures that our energy is going to be homegrown and that our economy is more than just resilient. that we will grow in the times of rapid change that are ahead of us. While the rest of the world waits for the future of energy, we're manufacturing it right here in New Zealand. We've moved from the sidelines to the forefront of the grid, and we're proud to be your partners in building that future. Thank you all for coming and sharing in this moment with us. Thank you. Now, I believe we have food and drink in our second little facility, 26.
Cool. Okay, that was the last speech.
Yeah, we got a bit ahead of ourselves.
Yeah, no.
The sentiment remains the same.
Yes.
Big wins all around. Living the dream. Okay, we've got a couple of tidbits to leave you with just before we sign out.
Yep, cool. So we've got one paper I'd like to point everybody towards to have a read if they enjoyed what they saw today. It's the paper on the actual whole junior experiment, which should hopefully be posted as a link into the chat very soon. So go have a look at that. It was written by Craig, our physics operator. He has done a bunch of work on that, but essentially summarizing all the stuff we've done so far, the entire team. Another one to look out for in the coming weeks. We have a fusion power plant design study coming out, which should answer hopefully a lot of questions about what questions people have about the dipole and how it sort of scales to a full-scale fusion power plant. So yeah,
cool.
That's going to be very exciting.
So the easiest way to keep track of what we're doing is following us on LinkedIn is the easiest way. We also have every 4-month newsletters that come out. You can sign up to those on the website. And then other than that, come take a look around, I guess. We do tours all the time. If you're ever in Wellington, send through an inquiry to OpenStar Inquiries. And then other than that, have a good day.
Have a good day. Thanks for watching.
Ciao.
It's been great.